Hello everyone and welcome. In this video I'm going to give you a complete course on basic algorithms and data structures. I'm going to start by explaining time complexity and asymptotic notation, and then we're going to move on to our first algorithm, binary search. After that, I will teach you every sorting algorithm you need to know. We'll start with basic algorithms such as insertion sort, selection sort, and bubble sort. Then I will take a break from sorting to explain recursion, a very important concept which unlocks some more advanced sorting algorithms such as merge sort and quicksort. Then I will introduce the first data structure called the heap and move on to heap sort, our last sorting algorithm. After that, we will mainly focus on data structures such as linked lists, hash tables, binary search trees, the queue, and the stack. You can use the timestamps I put in the description to jump around the video to the parts that interest you the most. I hope you enjoy, and let's get into it. So asymptotic notation is a way that we have to represent the time complexity of an algorithm, meaning the amount of time that it takes to run depending on the size of the input we feed into it. Now I think this is best explained with an example, so take a look at the code that I have here. We're going to have an input size which I've denoted by n. Now the algorithm itself consists of a for loop that goes to that same n, and inside it has two for loops that also go to n, and inside of both of those for loops we have constant time operations like printing and summing. So both of these are going to be constant time operations because the time they take to perform doesn't depend on the size of the input. It's always going to be the same. So how do we represent, the time complexity of this algorithm depending on how large n is, how large the input size is? So first of all, we're going to have some kind of constant, which is going to be, the amount of time that printing takes to run, and we're going to repeat that n times. So we're going to multiply this by n. Then we're going to add some other constant, which is the amount of time that this sum takes to run, and we're also going to do that n times. And both of these operations we're going to do n times because of the outer for loop. So we end up with an equation of this type. Now simplifying this, we have c1 plus c2 times n squared. And c1 plus c2 is just going to be, some other constant because both of those are constants. So I'm going to name it c, which is a generic constant, multiplied by n squared. Now in asymptotic notation, there are a few rules that we have to simplify expressions like these. So if you have some constant times n cubed plus, some constant times n plus some constant, we're only going to keep the fastest growing term. So what does this mean exactly? Well, the first thing, we're going to cut off all of the constants, right? Because if you have a really large number and you multiply it by some constant, that multiplication is not really going to make much difference in terms of the, order of greatness of that number. So we're going to cut all of the constants. And we're also going to only leave the fastest growing term, meaning the term that has the greatest exponent. Because it's the same thinking. If you have something really large and you add something that's not as large, it's just not going to make much difference. You might as well just keep, the one with the largest exponent. So we're going to cut n as well, and this can be simplified into n cubed. Since we're talking about time complexity and asymptotic notation, we would say that this algorithm has a time complexity of O of n cubed. So if we apply all of these rules into our little expression here, we're going to end up with a time complexity of O of n squared for this algorithm. And if we were to plot this on a Cartesian graph, we're going to have here the input size on the x-axis, which I've denoted by n in this case. And we're going to have the time on the other axis, and we're going to end up with quadratic time, which is just going to be, a parabola. Time can be negative, so we're only left with the positive side of the parabola. And this is O of n squared, and it's called quadratic time. We could also have something like this. This is going to be called linear time. It is just going to be a linear function, and this is O of n. And we can also have constant time. This is just going to be, some constant. And here we're going to say that we have an O of 1. Because like I told you, one of the rules of asymptotic notation is that you drop the constants when you're simplifying expressions, right? Now you could argue that this should be an O of 0, since, we have some constant, we drop it, we're left with nothing. However, this would mean that a certain constant time operation would take 0 time to perform. And that's actually not true, because every operation that we perform takes some amount of time, even if that time is constant. So for that reason, we say that we have an O of 1 for constant time. Now, in this algorithm, the only thing that's actually going to influence the time complexity is going to be n, right? It's going to be the input size. So let me show you another example where other factors come into play. So this is a linear search algorithm. In case you're not familiar with it, essentially we have an array, we have a certain element that we are looking for in that array. And with linear search, we're essentially sequentially looking at each element individually, checking if that element is, the target that we're looking for. If it is, we're going to return it. If not, we're going to go to the next element. And we're going to do this until the end of the array or until we find the element that we want, right? Now, in this case, added to the input size, we're going to have another factor that comes into play, which is the position of the element in the array, right? So in this case, we're going to have different cases. We're going to have a best case, and in this case, the element that we want is going to be the first element of the array, right? And in that case, we only have to go through one element. We only have to check it one time, and that's going to be great for us. So in this case, we're going to have constant time. We say omega of 1. So omega is going to be, the letter that we use to denote the best case. Then we're going to have an average case. So on average, the element that we want is going to be in the middle of the array, somewhere in the middle, and more or less at the position n divided by 2, right? So we're going to have to search n divided by 2 elements. However, like I told you, asymptotic notation rules, we drop the constants, so we're going to be left with a theta of n, right? Because we drop the half, and theta is the letter that we use to denote the average time complexity. And lastly, we're going to have our worst case. And the worst case is the element is going to be the last element in the array. So in this case, this means that we're going to have to go through every element of the array, and we're going to end up with an O of n, in which n is, the number of elements of the array. And for this, we use the letter O. So here we have 3 different types of asymptotic notation. We have big omega notation, big theta notation, and big O notation. Which one of these do you think is going to be the most important one to study? Well, you could argue that it is the average case, right? Because that's the most representative and probably the one that's going to happen in most cases. However, the worst case time complexity is actually the most important one because it's the one that's going to throw a threshold. It's going to draw a threshold to how slow your algorithm can be. And in most cases, that's the most important thing. So usually when you see time complexity analysis on algorithms, you're going to hear a lot about big O notation in worst cases and not so much about best and average. So again, if we draw this on the graph, we're going to have those same 2 axes. We're going to have a linear time, so this is linear search. And in case you don't know about it, there is another algorithm that's actually better than linear search, because linear search for really large arrays, it's actually going to be really slow. And we have an alternative called binary search. So binary search is going to essentially divide the array into 2 pieces each time. You don't really need to know how that works. You only need to know that it runs on logarithmic time. So this is going to be an O of log of n, which when n is really big is going to be significantly better than linear time, okay? Just so you know that this exists. In this vid, I'm going to explain binary search in the most simplified way possible. So let's get right into it. So imagine that you have this array right here and you want to search for a certain element. For example, let's make our target 15. So we want to know which index of the array holds the element 15. Now we could use an algorithm called linear search. And what this consists of is basically going through each element of the array individually and seeing if it is a target. So we would start here at the beginning. Then we would go to the second element, it's not equal, we go to the next element, it's not equal, we go to the next, and so on until we find our target. And this is going to give us a time complexity of O of n, where n is the number of elements in the array, right? Because we're going to have to look, in the worst case, through every element of the array before we find our target. Now, for this small array that I have right here, this is just fine. However, if you have a large collection of data, this is probably not going to be the best option. And that's where binary search comes in. Now, in order to apply binary search, your array has to be sorted, right? If it is not sorted, you have to either sort it first or you can't apply binary search. Now, the core idea is that we're going to have here two variables. One is going to hold the minimum. This is going to start out at the first element, and the other one is going to hold the maximum, and this is going to start out at the end of the array. Then we're going to calculate the middle position between our minimum and our maximum, and in this case it's going to be 11, right? Now we're going to check if 11 is greater than or smaller than our target. So our target is 15, and so 11 is smaller than 15. And since we know that our array is sorted, we know that the whole left side of the array here is not going to be our target, right? Because all of those elements are going to be smaller than 15. So we can automatically cut this side out of the array, right? And now we're going to move here our indexes. We're going to set the minimum to be right there, which is going to be mid plus 1 if you really think about it. And then the new mid is going to be the middle position between minimum and max, which is going to be 20. Now, is 20 greater than 15? Yes, right? So the whole right side of the array, all of the elements that are after 20 can be cut out, right? Because none of those elements is going to be our target. So we're going to delete the right side of the array like so. And now we have found our target, which is the only index that is left, which is going to be right here, 15. And this is how you apply binary search. Essentially, since the array is sorted, you're going to start out at the middle. If the element is greater, you can cut out the left side of the array. If it is smaller, you can cut out the right side of the array. And then eventually you're going to get to your target. And this is going to give us a complexity of O of log of n, which is much better than O of n for large collections of data. And keep in mind that this logarithm is of base 2 since we're dividing the array in each iteration. Now, I know a lot of people have trouble grasping this concept, so I would encourage you to think backwards, right? Imagine that you're multiplying each time by 2. So you have 2 by 2 by 2 by 2 by 2 and so on. And this is going to give us a power of 2, right? 2 to the power of n. Now, if you do the opposite and instead divide, you're going to have some random number, n divided by 2, divided by 2, divided by 2. And so this is going to give us a logarithm of base 2. So I hope that was easy to understand. And now let's get into the code implementation of this algorithm. All right, so let's get right into it. What I have here is a binary search function. This is going to take in our array, its size, and the element we're looking for. And this is also going to return to us an integer, which is going to be the index of that element in the array. So the first thing I'm going to do here is create a couple of variables, which is going to be the indexes. So our min is going to start out at the first element of the array. Our maximum is going to start out at the last element of the array. And then our mid is going to be the mid position between the minimum and the maximum. Now we're going to apply this algorithm a couple of times, and the condition for that is while our min is smaller than or equal to our max. So essentially, if our minimum hasn't surpassed our max, then I'm going to say that the mid is going to be our min plus our max divided by 2. So we're going to get the middle position between the minimum and the maximum. Now in here, we're going to have a couple conditions. So I'm going to say if the array at mid is equal to our target. So essentially, if we have found our target in the middle position, then we're just going to return mid, which is the index of our target. Now, else if the array at mid is smaller than our target, then this means that the left side of the array, we can just throw it out, right? Because the middle is smaller than the target, and so the target needs to be in the right side of the array. And what this means is that our minimum is going to change. And we're going to say that the minimum is going to be mid plus 1, like so. So this is going to cut out the left side of the array. And otherwise, then that means the opposite, right? So the array at mid is going to be greater than the target. And so what this means is that the maximum is going to be our mid minus 1. So we're basically going to cut out the right side of the array, and we're only left with, well, the left side of the array, right? Now, if none of these conditions are true, if we haven't returned our index, and if our minimum isn't smaller than or equal to our max, then that means we haven't found our element. We're just going to return -1 like so. All right, and this is our algorithm. I'm going to comment this line out. This is basically calling the binary search algorithm with our array. Its size is 7, and we're going to look for the element 6 here. Now I'm going to run this code, and this should hopefully give us 3, right? All right, and there we go. So 6 is here at the position 3. Now if I say, for example, 1, if I run this code, this is going to give me 0. Then if I say 11, it's the last element, this is going to give me 6. And if I say an element that doesn't exist, for example, 14, that's going to give us -1 because this element doesn't exist. In this video, I'm going to talk about the insertion sort algorithm. This is one of the most elementary sorting algorithms that exist, and it's really easy to understand and implement in code. So let's get right into it. We're going to sort this array right here using the insertion sort algorithm. So the base idea is that for each element, we're going to go over all of the previous elements. If we find a bigger element, we're going to swap the current with that element. If we find a smaller element, then we're going to end that iteration and go to the next element. So we're basically going to take each element and insert it in the right position, hence the name insertion sort. So let's do this with this array right here. We're actually going to start at the second element, so we're going to start out at 1. We're going to compare it with 3. Since it is smaller, we're going to swap those two, and we're left with 1, 3, 8, 10, and 5. Now, notice that for 8 and for 10, they are already in the correct position because the previous element for both of those is going to be smaller. So we're going to go directly to 5. We're going to compare it with 10. It is smaller, so we swap. It is smaller than 8, so we swap, and we end right there because 3 is going to be smaller. Then we are left with 1, 3, 5, 8, and 10, which is the sorted array. Let's do another example. Let's consider, for example, 8, 3, 1, 5, 4, and let's sort this using the insertion sort algorithm. We're going to start at the second element. We're going to compare it with 8. It is smaller, so we swapped. We're left with 3, 8, 1, 5, and 4. Then we go to 1. We compare it with 8. It is smaller, we swap. We compare with 3, it is smaller, we swap. We're left with 1, 3, 8, 5, and 4. We're going to do the same thing with 5. So we're going to be left with, so we swap with 8 and then we stop. We're going to be left with 1, 3, 5, and 8, and then 4. And then the last element, we're going to swap it with 8. We're going to swap it with 5, and we are left with 1, 3, 4, 5, and 8. So that is the insertion sort algorithm. Now let's talk about time complexity. So you might have realized already that we're going to have essentially 2 loops. In the outer loop, we're going to go through each element of the array, so we're going to have a complexity of n. And in the inner loop, we're going to go through every of the elements that are before that element. So first we're going to go through 1, then 2, then 3, so on until we go over n-1 elements. So this is going to leave us with a worst time complexity of O of n squared. Now, notice as well that if the array is already sorted, then even though we are still going through every element of the array in the outer loop, we're not going to do anything in the inner loop since we're not going to swap anything. And therefore, we have a best time complexity of omega of n. Now let's talk about stability. So as I mentioned in the previous video about selection sort, an algorithm is stable if the relative order of elements with the same key is preserved. So take this array right here. We have a 5, then a 3, then we're going to have a red 3, and then we're going to have a 1. So if insertion sort is stable, both in the beginning and in the end, the white 3 is going to come first and then the red 3. So let's apply the algorithm to this array. We're going to be left with 5. So 3 is smaller than 5, so we're going to swap. We're left with 3, 5, then the red 3, and then 1. And then we're going to go to this 3 right here, and we are left with 3, red 3, 5, and 1. And then we're going to go to 1. We are left with 1, 3, red 3 and 5. So this is the ending sorted array. Notice that the white 3 comes before the red 3, which means that this algorithm is going to preserve the relative order of elements of the same key, and therefore it is going to be stable. Now let's actually implement this in code. So I have the C++ file ready here. All I have is my main function where I have an array with 6 elements, and I'm outputting each element of that array. So this is the result for now. As you can see, it is insorted. Let's actually code here the insertion sort algorithm. So insertion sort, this is going to be a void function. It is going to take in the array we want to sort as well as its size. Now in here, I need 2 iterators, I and j, for both of our loops. And now let's iterate. So for I equals 1, we're going to start out at the second element of the array. I is smaller than size I++. So we're going to go over every element of the array. Let's create here a current, which is going to hold the array at index I, so the current element we are at. Then let's start j at I-1, so at the previous element. And now let's loop again. I'm going to say while -1 is smaller than j. So while we haven't reached the end of the array, essentially, and this is not a semicolon, this is an end, the array at index j is greater than the current element. So while we haven't reached the end of the array and the current element we are at is greater than the array at the position I, we are going to swap, right? So we're going to say array at j plus 1 is equal to the array at j, and we're going to decrease j like so. Then in the end, all we have to do is say that the array at j plus 1 is going to be the current, which is array at index I. And this is actually going to complete our algorithm. So as you can see, we are iterating through every element of the array. We are storing that element in this current variable. Then we are iterating through the previous elements of that array and swapping them accordingly. And then we're going to put the current element at the last index that we're at. Okay, so now let's actually apply this algorithm to our array. Let me pull this up. I'm going to run this. And as you can see, now the elements of my array are sorted. In this video, I'm going to talk about the selection sort algorithm. This is one of the most elementary sorting algorithms that exist, and even though it is not the most efficient for large datasets, given its complexity, it is still really useful to know because it's really easy to understand and implement in code. So let's actually get into it. We're going to sort this array right here using the selection sort algorithm. So the base idea is that we're going to iterate through each element of the array. So we're going to start out at 3. And then we're going to iterate through the rest of the elements that are after that element. We're going to find the minimum in that set of elements, and then we're going to swap the current element with the minimum, like so. So in the first iteration, this is going to leave us with 1, 5, 10, 3, and 8. So we swapped 3 with 8. Then we're going to go to 5. We're going to find the minimum, which is 3, and we're going to swap those two. So we're left with 1, 3, 10, 5, and 8. And we're going to repeat this until we have the sorted array. So we're going to go to 10. The smallest element after 10 is 5. So we're going to swap those two. We're left with 1, 3, 5, 10, and 8. And lastly, we're going to swap 10 and 8. So we're going to be left with 1, 3, 5, 8, and 10, which is the sorted array. So now let's talk about time complexity. In the first loop, we're going to iterate through n elements, and in the second loop we're going to iterate through n-1, then n-2, then n-3, and so on until 1, right? So this is going to give us a worst time complexity of O of n squared. And in the best case, we're going to have to do the same thing, because even though we might not be exchanging any elements, we're still going to have to go through every element of the array in the first loop and n-1, n-2, and so on in the second loop. So for the best case, we're going to have an omega of n squared. And since we have an O of n squared and an omega of n squared, this is going to leave us with a theta of n squared. Okay, now let's talk about stability. So an algorithm is considered stable if it preserves the relative order of elements with the same key. So take this example. We're going to have a white 3, then we're going to have a red 3, and then a 1. This is going to be our array. Let's apply the selection sort algorithm here. So we're going to go to 3, we're going to find the minimum, which is 1, and we're going to swap both of those. So we're going to get 1, red 3, and then the white 3. And this is our final sorted array. So as you can see in the beginning, the white 3 comes before the red 3. However, after we apply the algorithm, the red 3 comes first. So this proves that the algorithm is not going to be stable, right? Because the elements with the same key, in this case, both of the 3s, are going to be exchanged. Their relative order is going to be altered, and therefore this algorithm is not going to be stable. Now, that's enough for theory. Let's actually implement this in code. In order to do that, I'm going to be using C++. However, you don't need to know C++. All I ask is that you're comfortable with the basics of programming. So I have this C++ file ready here. Let's create a new void function called selection sort, like this. It is going to take in the array that we want to sort and also the size of the array, so the number of elements. So in here, let's actually code the selection sort algorithm. We're going to start with 2 iterators, I and j, and then we're going to have a minimum, which is going to be the index of the minimum element of each subarray that we're going to go through. Then we're going to iterate. So for I equals 0, we're going to start at 0. We're going to go to the end of the array, then I++. We're going to set the min to I. So by default, the minimum element is going to be the first element we're at. Then we're going to iterate through the rest of the elements, starting at I+1, going to the end of the array, j is smaller than size, and j++. Then we're going to check if the current element we're at is smaller than the element at the minimum index. So if the array at index j is smaller than the array at the minimum index, we're going to set the minimum index to be j. So basically, if we find an element that is smaller than the current element at the minimum index, we're going to say that the minimum index is going to be the index we're at. Then in the end, we're going to swap these two. So I'm going to say temp. I'm actually going to go here and say temp after min. So temp is going to be the array at the index I. So this is going to be the element that we're currently at. And then I'm going to say that the array at the index I is going to be the array at the index min. So we're going to basically put the minimum element in the I position. And then I'm going to say array at min is going to be temp, which is array at index I. So we're going to basically change those two. So that's going to be it for our selection sort algorithm. Now let's actually apply this here. So I'm going to say int r. This is going to have 9 elements, for example. So we have 1, 2, 3, 4, 5, 6, 7, and 8. And 9. Okay, so 9 elements. Then we're going to say for int I equals 0, I is smaller than 9, I++. We're going to see out the array at the index I and a \n. However, before this, we're going to apply the selection sort algorithm on our array, and it has a size of 9, and this should print the elements of the array in a sorted order. So I'm going to run this, and as you can see, this prints the elements of the array in a sorted order, so our algorithm is correct. Now let me show you another way we can do this. I'm actually going to ask for some user input, so I'm going to say int n. I'm going to cin n. This is going to be the size of the array. Then I'm going to say array with the size n for int I equals 0, I smaller than n, and I++. I'm going to cin the array at position I. So I'm going to ask the user to input the elements of the array. Then I'm going to apply the selection sort algorithm to the inputted array that has size n. And then I'm going to say for int I equals 0, I is smaller than n, I++. I'm going to see out the array at the position I and a \n. And let me pull this up. I'm going to run this code. It's going to ask us for some input. I'm going to say, for example, 9. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if I run this now, this is going to output all of the elements that I inputted in a sorted manner. In this video, I'm going to explain the bubble sort algorithm. This is a very simple and elementary sorting algorithm, really easy to understand, so let's get right into how it works. So, assume we have this array right here and we want to sort it using the bubble sort algorithm. How's this going to work? Well, we're going to go over every single element of the array starting at the first element, which is 8, and we're going to compare successive elements. So we're going to compare 8 with 3. 3 is smaller than 8, so we're going to swap those two and we are left with 3, 8, 5, and 1 that remain unchanged. Then we're going to compare 8 with 5. 5 is smaller, so we're going to change those two. We're going to be left with 3, 5, 8, and 1. Then we're going to compare 8 with 1. 1 is smaller, so we're going to change those two, and we are left with 3, 5, 1, and 8. So this is the first iteration of the algorithm. And notice that basically what we did is we took the biggest element of the array and we pushed it to the end. Now we're going to do the same thing for the element 3, for example. So we're going to compare 3 with 5. 5 is greater, so we're going to leave it as it is, 3, 5, 1, and 8. Then we're going to compare 5 with 1. 1 is smaller, so we're going to exchange those two. And now this is the second iteration. What we did is we took the second largest element of the array and we pushed it to the end. And now we're going to do the same thing with the rest of the elements. We're going to compare 3 and 1. 1 is smaller, so we're going to exchange those two, and we are left with the sorted array. So this is how the bubble sort algorithm works. Basically, we're going to compare successive elements of the array and exchange them if we have to. Now, let's talk about the time complexity of this algorithm. So, as you can see, we're going to have an iteration, since we're going to go over every single element of the array, and then in each of those iterations, we're going to have first n-1 comparisons, then we're going to have n-2 comparisons, we're going to have n-3, and so on until we get to 2 comparisons, and finally 1 comparison, and then we are done. So this is going to leave us with a time complexity of O of n squared in both the worst and average cases. Now let's talk about how to actually implement this algorithm in code using C++. So I am here at VS Code. Let's actually implement the bubble sort algorithm. All I have here is the bubble sort function. This is going to take in the array that we want to sort and the size of that array. And then I have my main function where I have the array that I actually want to sort and a little loop that's going to print all of the elements of my array. So let's get started. The first thing is I'm going to create a temporary variable here, and then I'm going to create 2 loops. So I'm going to say for int I equals 0, I is smaller than size, and then I++. This is going to be the outer loop that's going to go over every element of the array. And then for int j equals 0, j is smaller than the size minus I minus 1. And here the reason we're doing minus I is we're not going to compare with every single element. We're only going to compare with the elements that are not yet in their correct position. And for that reason, we have to do size minus I so that we don't do unnecessary comparisons. And then of course increment j. And now let's compare. So if the array at index j plus 1 is smaller than the array at index j, then that means that we need to exchange those two. So I'm going to say temp equals array at index j, then array at index j equals array at index j plus 1, and then array at index j plus 1 is going to equal temp. So we're going to exchange those two elements, like so. And this actually concludes our bubble sort algorithm. It is really that simple. Let's actually use it down here. So I'm going to say bubble sort with the array. The size is going to be 6. Let's just hard code that in there. And now I'm going to run this code. Let me pull this up so that you can actually see. And as you can see, all of the elements of my array are going to be in the correct position. Now, the nice thing about the bubble sort algorithm is that you can also change the way that you're sorting very easily. So for example, if I do, instead of array j plus 1 array j, I'm going to do array j and then array j plus 1. And if I run this now, as you can see, the array is going to be sorted in the opposite order. So really fun algorithm. And there's also another optimization that we can do, which is we can add a Boolean variable here called done, which is going to be false. Then each iteration, we're going to set done to true at the beginning. However, if we make any exchanges, we're going to say that done equals false. And then down here, all we have to do is say if we are done, then we break out of the loop. And this is going to keep us from making unnecessary comparisons, right? So from the moment that we don't have any exchanges happening, we know that our array is sorted and we don't need to keep going with the algorithm. So we're just gonna break away from it, right? And if I run this now, as you can see, this is going to output the exact same thing. Recursion is a very important programming concept. It appears in various important algorithms, and once you get it down, it's really not that hard to understand. So I think recursion is better explained with an example. So take the factorial function, for example. The factorial function, what does it do? Well, it takes every number between 1 and a certain number, and it basically multiplies them together, right? So for example, the factorial of 3 is going to be 3 times 2 times 1, right? And this is going to be 6. However, if you really think about it, the factorial of 3 can be broken down into smaller calls of that same function, of the factorial function, right? Because the factorial of 3 is actually 3 times the factorial of 2, right? And the factorial of 2 is 2 times the factorial of 1. So this is going to be 3 times 2, and then the factorial of 1 is just 1, and this is going to be 6, right? So this is basically what recursion is. It's basically a function that calls itself because there are certain values of that function that depend on previous values, on smaller calls of that function. And when you have a recursive function, there's usually going to be a case, well, not usually, there's always going to be a case that doesn't depend on previous values of that function. In this case, this is going to be the factorial of 1, right? Factorial of 1 doesn't depend on anything. It's just 1, right? It's just the value 1. And this is what's going to be called the base case. Now, keep in mind that any recursive function can also be implemented iteratively. However, recursion offers you a more elegant and simple way to do things. So let's actually define here the factorial function with some pseudocode. So I'm going to say define the factorial of n, and I'm going to say return that same n times the factorial of n minus 1, right? And this is going to be the recursive case. It is the recursive case, which is the case that actually depends on previous values, right? However, we don't want to do this forever because we don't really want to go into 0 or the negative numbers, right? We only want to do this until we reach the base case, which is going to be our stopping condition. So up here, I'm going to say if n is equal to 1, which we already saw is our base case, I'm just going to return 1, right? Because factorial of 1 is just 1. And otherwise, I am going to do the recursive case. So this is going to be the base case, and this is going to be our recursive case. And this is basically what our factorial function is going to look like in a recursive approach, right? So we have our base case, our stopping condition, and then we have our recursive case. Now let's actually see what happens when we call this function, right? Because you might be wondering, well, if certain values depend on previous calls of that function, then how does this all work? So when we call the factorial of 3, there's something called the call stack, right? This is basically going to contain all of the calls of our function. So when we call the factorial of 3, we're going to add another frame to our call stack, which is going to be the factorial of 3, right? And the factorial of 3 is going to calculate the factorial of 2. So the factorial of 3 is going to add the factorial of 2 to the call stack, right? Another frame to the call stack. And the factorial of 2 is going to calculate the factorial of 1. So that's going to be added to the call stack as well, right? So now we have all the frames we need in our call stack. all we have to do is go back down and calculate those values. So the factorial of 1, our base case, is just going to be 1. And then the factorial of 2 is going to be 2 times the factorial of 1, which we've already calculated, and this is going to be 2. And then the factorial of 3 is going to be 3 times the factorial of 2, which is 2. And so this is going to be 6, right? So when we call a recursive function, we're going to add frames to our call stack. So every time we call our function, we add another frame to the call stack. And then all we need to do is erase them one by one in the reverse order and calculate the values that we need. So I wanted to show you another example before I finish the video, which is the Fibonacci sequence. You're probably familiar with this, but if you're not, it's basically a sequence of numbers where each number is the sum of the two previous numbers in the sequence, and the Fibonacci of 0 and 1 are the base cases. So the Fibonacci of 0 is just 0, that's the first number in the sequence, and the Fibonacci of 1 is just 1, that's the second number of the sequence. So now we're actually going to have two different recursive cases. If n is equal to 0, then we're going to return 0, the first element in the sequence. And if n is equal to 1, then we're going to return 1, which is the Fibonacci of 1. And otherwise, we're going to have our recursive case. And our recursive case is going to be the Fibonacci of n minus 1 plus the Fibonacci of n minus 2, right? The sum of the two previous elements in sequence. And this is basically the Fibonacci function done recursively. It's very simple. It has two base cases and then the recursive case, which is just calling the sum of the previous values. Now I have this for loop here, which is going to print the first 10 Fibonacci numbers. Let me just run this code right here. And as you can see, the first 10 Fibonacci numbers are going to be these. So merge sort is a divide and conquer type of algorithm. This means we're going to split our main problem into smaller subproblems, solve those subproblems, and then merge the solutions back together to solve the original problem, hence the name merge sort. Now, suppose we have this unsorted array. We're going to successively split it until we're left with two element arrays, which we're then going to sort by direct comparison of those elements. Then all we have to do is merge these subarrays back together in a sorted manner until we reach the final sorted array. Now let's talk time complexity and use cases. I'm going to provide a comparative analysis between merge sort and two of the most well-known sorting algorithms, quicksort and insertion sort. Merge sort has a time complexity of O of n log of n in both the worst and average cases, whereas quicksort and insertion sort are on average O of n log of n and O of n respectively, and worst cases of O of n squared. Now, as for when you should use them, based on their complexities, merge sort is usually better for linked lists, while quicksort is usually better for large and really unsorted arrays. Although if it is really well optimized, it is usually faster than merge sort in most cases. Insertion sort, on the other hand, although seemingly has a worse time complexity in both average and worst cases, still has its uses, for example when you have small or somewhat already sorted arrays. Now let's actually implement the algorithm. As you could probably already tell, we're going to implement a recursive solution which is going to work by branches. So we're going to create various branches with the divide and conquer strategy and work on them in parallel. So now I'm here at VS Code and I'm actually going to explain the code for this algorithm. So I have here three functions. First, my merge function up here. This is going to actually merge the subarrays back together. And it's going to take in our original array and a few indices, which are going to be the left, the middle, and the right. And then the merge sort function is going to split our array into pieces until we can't split it anymore. And it's going to take in our array and the indices start and end. So let's actually code this merge sort function. So we're going to keep splitting the array until our start is greater than the end. So I'm going to say if the start is greater than or equal to the end, then we're done, right? So we're just going to return like this. And otherwise, I'm going to create here a variable which is going to be called mid, and this is going to be the middle index of our array. So this is going to be end minus the start divided by 2, like so. And now I need to call this merge sort function again for the left side of our array and for the right side of our array so that we can keep splitting it. So I'm going to say merge sort,
and this is going to take in our array again. And now the start is going to be start, and the end is going to be the mid. And this is array, like so. So this is going to get the left side of our array. And then merge sort, but this time the array is going to be the same, and the start is actually going to be mid plus 1, and the end is going to be the end. So this is going to get the right side of our array. And in the end, I need to merge them back together. So this merge function takes in our array, it takes in a left, which is going to be our start, a middle, which is going to be our mid, and a right, which is going to be our end. Okay, so this is going to conclude the merge sort function, where we're going to split the array into smaller arrays. Now let's actually code the function where we're going to merge those arrays. So first of all, I need to create the left array and the right array. So I need a left size and a right size. So I'm going to say int const, and this is going to be the left size. And this is going to be the middle minus the left, like so, plus 1. And I'm going to copy this. And this time it's going to be the right side. So instead of left, this is going to be right. And the right size is going to be our right, like so, minus the mid. Okay, now I'm actually going to create these arrays. So I'm going to say int, and this is going to be the left array. There's going to be new int, and the size is going to be left size. And then we're going to create another array, which is going to be the right array, and it's going to be equal to new int, and the size is going to be right size. Okay. Now I'm actually going to copy the data from our array, from our original array, to the left array and to the right array. So I'm going to say for int I equals 0. While I is smaller than the left size, let's increment I. And here I'm going to say that the left array at the index I is going to be our original array, and the index here is going to be left plus I, like so. And now I'm going to grab this, and I'm going to do the same thing for the right array. So instead of here being left, all of these are going to be right. And now the index actually is not going to be right. It is going to be mid plus 1 plus I, like this. Now, I'm going to create here a few variables, which are going to be the indexes of our array. So I'm going to say int left index is going to start out at 0. The right index is going to start out at 0. And the array index is going to start out at left. Okay, now I actually need to merge the temporary arrays back into the original array. So in order to do that, I'm going to create a while loop. And I'm going to say while the left index is smaller than the left size, and the right index is smaller than the right size, then I'm going to keep applying this little algorithm. So I'm going to say if the left array at the left index is smaller than or equal to the right array at the right index, then in this case, I'm going to say that the array at the array index is going to be the left array at the left index. And I need to increment the left index. So left index plus plus. And otherwise, so else, we're going to do the opposite. So I'm going to copy this. I'm going to paste it right here. And I'm going to change everywhere that says left to be right, like so. And in the end, I need to increment the array index. So array index plus plus. And this concludes this part. Now the next part is we're going to copy the remaining elements of the arrays, if there are still any, into the original array. So I'm going to start with the left array. I'm going to say while the left index is smaller than the left size. And in here, I'm going to say that the array at the array index is going to be the left array at the left index, and left index plus plus. So we need to increment left index, and we need to increment array index. and this is array, like so. And now I'm going to do the same thing for the right array. So I'm going to copy this. Oops, what did I do here? Okay, array, like this. Sorry about that. So I'm going to copy this. Now it is correct. And I'm going to paste this. And everywhere it says left, I'm going to say right. And this basically concludes our algorithm. Now the last thing I need to do is I need to delete our temporary array. So I'm going to delete the right array. And I'm going to delete the left array, like so. And we're done. Okay, so let's actually call this down here. I'm going to say merge sort, and this is going to take in our array, and then it's going to take in a start, which in the beginning is going to be 0, and then an end, which in the beginning is going to be the size of the array minus 1. So let's actually create this. I'm going to say int size is going to be the size of the array divided by the size of the array at the first index, like so. And we need a semicolon here. And now I'm actually going to print the element. So I'm going to say for int I equals 0, while I is smaller than the size I++. And I'm going to see out the array at index I and a \n, like so. Okay, and we're actually done with everything. I'm going to run this code. Let's see if our array is sorted. Hopefully it is. And okay, as you can see, our array is completely sorted. So our algorithm works.
In this video, I'm going to teach you the quicksort algorithm. This is a divide and conquer type of algorithm, meaning we're going to split our main problem into smaller subproblems, solve those subproblems, and then merge the solutions back together in order to solve the original problem. And we're going to do this recursively. This is a very efficient algorithm. In some programming languages that have a built-in sorting algorithm, it is usually a variation of the quicksort, and it's really not that hard to understand. So let me tell you all about it and how it works. So I'm going to sort this array right here using the quicksort algorithm. The first step is to choose a pivot. Now I'm going to choose 8 here as my pivot, and I'm going to leave it at the far right of my array. Then I'm going to take the rest of the array and I'm going to put the elements that are smaller than our pivot on the left of the array and the elements that are greater than our pivot on the right of the array. Now, how am I going to do that? Well, I'm going to have 2 iterators, I and j. I is going to start out at the far left of my array, and j is going to start out at the far right of my array. I is going to look for elements that are greater than our pivot, and j is going to look for elements that are smaller than our pivot. So I is going to go to the right, is going to go to 12. 12 is greater than 8, so we're going to leave it there. We're going to do the same thing for j. j is going to go to 6. 6 is smaller than 8, so we're going to leave it there. And now that we have I and j in their correct positions, we're going to swap the elements in those positions. So 6 is going to go to the place where 12 was before, right here, and 12 is going to go to the place where 6 was before. Now I is going to move here, 7 is smaller than 8, so we continue moving, and then 9 is greater than 8, so I is going to stay here. J was originally here, and so it moves to the left. 14 is bigger than 8, so we keep going. 9 is bigger than 8, so we keep going, and then we stop at 7. Now, at this point, the paths of my iterators have crossed, right? So instead of swapping the elements in those positions, I'm actually going to take the element in the position I, and I'm going to swap it with the pivot. I'm going to put 8 here, and I'm going to put 9 over here. And now I have split my array into elements smaller than 8, or equal to 8, and elements greater than 8, right? This is called doing a partition. It's basically breaking the array into 2 pieces, in which one is elements smaller than the pivot and the other is elements greater than the pivot. Then I'm going to take both of these partitions and apply the exact same algorithm. Now, notice that this partition is already sorted, right? So I'm actually not going to go over the process of sorting this because, well, it doesn't really make sense. I'm going to go to this partition right here and apply the same algorithm. I'm going to choose, for example, 12 as my pivot. So let me just copy this over here, 13, 9, and then I'm going to put 12 at the far right of my partition. And now I'm going to sort this partition. I is going to go here. 14 is greater than 12, 9 is smaller than 12, so we're going to swap those two. I'm going to put 9 over here and then 14 over here. Then both I and j are going to go to 13. 13 is greater than 12, so our iterator j is going to go here. And since our iterators have crossed paths, I'm going to take the iterator I, and I'm going to put the pivot right there, and I'm going to put 13 right there. So now we have two sorted partitions, and basically all we need to do now is merge our partitions together, right? So we're going to have this partition up here, which is going to be 3, 6, 7, 8. Then this partition right here, which is 9, 12. And then this partition right here, which is not yet sorted. However, we would sort it eventually during the algorithm, and we end up with 13 and 14. And this is going to be our sorted array. This is going to be the quicksort algorithm. So now let's talk about the algorithm's time and space complexity. So time complexity first. On average, this is going to have a complexity of O of n log of n. Well, why is this going to happen? Well, that's because if everything goes according to plan, we're going to successfully split our array into halves, right? Into partitions which are going to be halves. And so that's where the log of n comes from. And then to actually sort those partitions, we're going to have to go over the elements one by one. So that's going to have a complexity of n, right? So for that reason, on average, this is going to be O of n log of n. However, in the worst case, this is actually going to be an O of n squared. Now, I would encourage you to try to figure out why that happens, but basically assume that in every iteration of the algorithm, our pivot is going to be the biggest element in the array. Well, that means that we're going to end up with one partition that has the pivot, the only biggest element, and another partition which is going to have the rest of the elements of the array. Right? And if this happens in every iteration of the algorithm, we're going to have to handle the elements one by one when we're splitting the array into partitions. So this is going to give us a complexity of n squared. Now let's talk about space complexity. So even though we're not using any extra space for the array itself, we are doing a recursive function, right? So we're actually adding frames to the call stack, which takes up memory, right? So in the worst case, the space complexity of our algorithm is going to be O of n, right? Because of the same reason why the time complexity in the worst case is n squared, right? Because if the pivot is always the biggest or the smallest element of the array, we're going to have to split the array n times instead of only splitting it log of n times, right? And on average, this is going to be then log of n, right? Because if everything goes to plan, we are splitting the array into halves in every iteration, which is going to give us a complexity of log of n. Now let's actually implement the quicksort algorithm in C++. Alright, so I'm here at VS Code. Now let's actually implement the quicksort algorithm. This is going to consist of two functions, one which is going to be sort of the main quicksort function. This is going to be the recursive part of our algorithm where we're only going to call this algorithm again with the partitions that we create. And the partition function is sort of going to be a helper function where we're going to do all of the process of incrementing and decrementing the iterators and swapping the elements that we need to swap. So I'm actually going to code the quicksort function first. As I said, this is going to be a recursive function. So the first thing we're going to do is our base case. And our base case is going to be, well, let me just say that this function is going to take in the array that we want to sort and the indexes between which we want to sort it. So left and right. So I'm going to say if right is smaller than or equal to left, then we're just going to return, right? Because if right is smaller than or equal to the left, then that means that we can't really break our array into any more pieces, into any more partitions. And so we're just going to terminate the algorithm, right? Then I'm going to create here an integer, which is going to be our pivot. And this is actually going to be returned by our partition function. This is also going to take in our array, our left, and our right, like so. And now, since this is a recursive function, I need to call the quicksort function with the left side of our array, so from left to pivot -1, and to the right side of our array, so A, and this is going to be pivot +1 and right. So this is the quicksort function. Notice that we're not using any extra memory, we're only basically applying the algorithm in different parts of our array, so to the left side of our array and to the right side of our array. We don't necessarily need any more memory. Now let's actually code here the partition function. This is also going to take in the array we want to sort and the indexes between which we want to sort it. So first of all, let me create our iterators. I is going to be left -1, and I'm running out of battery. Sorry about that. Then J is going to be right. And now we need our pivot. So our pivot is going to be the last element of our array. So the array at the index right. Then we need a temporary variable with which we're actually going to perform these swaps. And those are all of the variables that we need. Now our actual algorithm is going to be a while loop. So while I is smaller than J, we're going to increment I, right? So how are we going to do that? I'm actually going to use a while loop. I'm going to say A at ++I is smaller than the pivot. And I'm just going to end this here, right? This while loop is just going to have this one line. Basically, while the index I of my array is smaller than my pivot, I'm going to increment it, okay? And then I'm going to do the same thing for J. So while our pivot is smaller than A at index -J. And in here, we actually need to protect ourselves from the case where J is equal to left. So if J is equal to left, then that means that we can't really walk any further left, right? Because we're going to go out of bounds of our array. And so I'm just going to say break here. So now we have our iterators in the correct position. All we need to do is swap. So if I is smaller than J, basically if we haven't crossed paths, right, if our iterators haven't crossed each other, then we're going to swap. So temp equals AI, AI equals AJ, and AJ equals temp, like so. And once we're done with this, we only need to put basically our pivot in the index I, right? So I'm going to say temp equals AI, and then AI equals A right, which is our pivot, and then A right is equal to temp, like so. And we're actually done with our algorithm. Now, as I said, the partition function is going to return the new position of our pivot, so all we need to do is return I. Then we're going to go back down to our quicksort function, and we're going to apply this algorithm to the left side of our array, or to the left side of our pivot, and to the right side of our pivot. And that is basically all that we need for our quicksort function. Now in my main function, I actually have here the array that I want to sort, its size, and I have here a for loop that's going to print the elements of that array. Now down here, I've already printed our array. It is obviously not sorted yet. So let's apply the quicksort algorithm here. So this is going to take in the array that we want to sort, then our left, which is going to be 0, and then our right, which is going to be size -1. Now, if I run this again, notice that our array is now going to be, sorted, as you can see. In this video, we're going to talk about the heap data structure. I'm going to explain what it is, how to create a heap from an array, and then I'm going to give you a code example of all of the algorithms we're going to implement. So first of all, what is a heap? Well, essentially, a heap is a tree-like structure in which every child is smaller than its parent. And what does this mean in practical terms? Well, first of all, it means that the top of the heap, which is called the root, is the largest element in the heap. And it also means that as you go down in the heap, the elements get smaller and smaller. Now, a couple of technical terms before I actually explain how to create a heap. First of all, each element of the heap is going to be called a node. So these are nodes. The root is a node, for example, and it has 2 children. It has 9 as its left child and 14 as its right child. And then we also have elements that don't have children, and these are called the leaves of this heap. So Let's learn how to turn this array into a heap data structure. We're going to use the heapify algorithm to do this. This is the core algorithm. And then we're also going to use the build heap, which is just basically calling heapify a bunch of times. Now, the first thing we're going to do here is grab this array and display its elements in a tree-like structure from top to bottom and from left to right. So 2 is going to be at the root, and then its children are going to be 16 and 12. And then their children are going to be 11, 15, 7, and 6. And then their children are going to be 10 and 20, and there are no more children. Now, this is obviously not a heap, so let's learn how to apply heapify to turn this into a heap. So heapify is a recursive algorithm, and we're going to start out at the lowest level in the heap in an element that is not a leaf. So in this case, we're going to start out at 11. Then we're going to compare 11 with its children, and we're going to find the largest child. If the largest child is greater than the parent, we're going to exchange those two. Now 20 is obviously greater here than 11, so we're going to change those two. 11 is going to go here, 20 is going to go here. Now 11 is at its new position. Does it have any children? No, so we can move on. We're going to go now to 16. Does it have a larger child? Yes, it does, 20, so we're going to exchange those two. Now, does 16 still have a larger child? No, it doesn't. So we're going to move on to 2 here. So 2 obviously has a larger child. We're going to exchange 20 and 2. Now, does 2 still have a larger child? Well, yes, right? It's 16 and 15 are both larger than 2. So we're going to have to reapply heapify to 2. And we're actually going to pick 16 here, which is the largest. So we're going to exchange those two. Now, does 2 still have a larger child? Yes, it does. We're going to pick the largest, which is 11, and we're going to exchange those two. And now, does 2 have a larger child? No, it is already in its correct position, and so we have created a heap successfully. So the heapify algorithm is the process of individually comparing each element with its children and exchanging if need to, and the build heap algorithm is going to do this for the nodes that needed to be done. So the end result of this array is going to be 20, 16, 12, 11, 15, 7, 6, 10, and 2. So this is going to be the final result here, and this is how our array is going to be displayed in the end. Now let's talk about a couple of more things. So first of all, given a certain node at index I, we know a couple of things about its parent and about its children. So the first is its parent is going to be at the position I plus 1 divided by 2 minus 1. We also know that its left child is going to be at I times 2 plus 1. And we also know that its right child is going to be at the position I times 2 plus 2. And these are formulas that we know, right? We are certain of this, and we can use this anytime we want. Now, this only works for 0 indexed heaps. This means that the indexes start at 0 and the root is at the index 0, okay? And the last thing I want to talk about before we get into the code is going to be the time complexity. So first of all, heapify. The time complexity of this is going to be log of n, right? So to put each element in its correct position, we're going to have to go through, in the worst case, a branch, right? An arm of the tree. And so this is going to give us log of n. And then we have build heap. And the complexity of this is going to be n, which is the number of nodes that we have in our heap. So this combined is going to give us a complexity of O of n log of n in order to build a heap. And that is all I wanted to talk about for the explanation. Now let's get into the code. Alright, so I'm here at VS Code, and let's actually apply the algorithms that we've learned. The first one I'm going to do is going to be heapify. This is going to take in our array, the heap size, which is really just the length of the array, and the index to which we're going to apply this algorithm. Now in here we need a couple of variables. I'm going to create a largest equal to I in the beginning, and a temporary variable for when we have to exchange. Then we need the children here of our node. I'm going to say that the left is going to be I times 2 plus 1, and the right is going to be I times 2 plus 2, like so. So that's going to be the left and the right index, and these formulas work for 0 indexed heaps. Then I need to check which one of the children is the largest, because that's the one we're going to exchange with. So I'm going to say if left is smaller than or equal to the heap size minus 1, and the array at largest is smaller than the array at left, then I'm going to set the largest here to be the left. So basically what this means is if left is a valid index of our array, if it is smaller than or equal to heap size minus 1, and the array at largest is smaller than the array at left, then that means that the largest is the left, right? And we're actually going to do the same thing for right. So I'm actually just going to copy this, paste it, and I'm going to change here left to right, like so. So now largest is going to contain the largest child, right? Then I'm going to say if our largest is different than I, so if we've actually picked a child, if we actually have a child that is larger than our parent, then we're going to exchange. So I'm going to say temp equals AI, then AI is going to be A at largest, largest, like that. And then our A at largest is going to be our temp. All right, so we've exchanged, and now heapify is a recursive algorithm. So we're actually going to apply here heapify with the same array, same heap size, and now the new index is going to be largest, like so. So that is the heapify algorithm. Now inside of our build heap, we're going to take in the array and the heap size, and in here we're basically just going to apply the heapify algorithm for a bunch of nodes. So I'm going to say for int I is equal, and we're going to start this at heap size divided by 2 minus 1. Then I is greater than minus 1, and I minus minus. So we're going to start at this index, and this is going to exclude the leaves because we don't want to apply heapify to those. And it's going to decrease I until minus 1. We're just going to apply here our heapify algorithm to the array with the heap size and with the node I. So that actually concludes the code for the build heap. Let's actually apply this down here. I'm going to say that int heap size is going to be the size of the array. In this case, it's 10. And then I'm going to apply heapify, I'm going to apply build heap, like so, to our array with our heap size. And then we have a for loop here, which is going to output the array. And I'm actually going to run this. I'm going to pull this up. And as you can see, now we have the root here at the first index and then the rest of the heap. And this is actually the same as the explanation that I did manually. So that is the build heap algorithm. That is how you construct a heap with code. And in the next video, we're actually going to use this to construct the heap sort algorithm. So basically, a heap is a tree-like structure in which the parents are always greater than its children. So this means that the largest element is going to be at the top of the heap, which is called the root. And it also means that as you go down in the heap, the elements get smaller and smaller. And we can actually use these properties of the heap to construct an efficient sorting algorithm called heap sort. So this is what this array looks like when I display it in a heap. And now how do we actually use these properties to sort the array? Well, first of all, we know that the root has the biggest element. So we're actually going to remove the element of the root. I'm going to delete this, and we're going to exchange it with the last element of the heap, which in this case is going to be 2. Okay? Now, this obviously disrupts the characteristics of a heap because the root no longer has the greater element. And so we're actually going to have to apply here an algorithm called heapify. And what this does is it takes a node, it compares it with its children, and if it has larger children, it will choose the child which is the largest and exchange it with the node itself. So we're actually going to pick here 16, and we're going to change this with 2. So 16 goes here and 2 goes here. Now, does 2 still have larger children? Well, yes. So we're going to have to apply heapify one more time, right? This is a recursive algorithm. So we're going to choose the largest child. This is going to be 15. So we're going to exchange those two. 2 is going to go here and 15 is going to go here. And now we are back to having a heap, right? The largest element is at the root, and as we go down, the children get smaller and smaller. So we're going to reapply this algorithm. We're going to remove 16 here from the heap, and we're going to exchange it with the last element, which is 10. And now we need to apply heapify. So we're actually going to exchange 15 and 10 because 15 is the largest child. So we're going to have here 15 and 10. Does 10 still have a largest child? Yes, it does. 11 is larger than 10. So we're going to put 11 here and we're going to put 10 here. So now we have a heap again, and we have the largest element at the root. Then we're going to do the same thing for 15, right? Then we're going to go to 12, then we're going to go to 11, then 10, 7, 6, and 2, and there we have it, our sorted array. So that is the heap sort algorithm. It's actually pretty simple. Now let's talk about its time complexity. So heapify is going to have a time complexity of log of n. Why? Well, that's because in order to put an element in its correct position, we're going to have to apply this algorithm to basically a branch of the heap, right? To an arm of the heap. And so this is going to have a complexity of log of n. And then for the actual heap sort algorithm, we're going to apply this n times. So in the end, we have a time complexity of O of n log of n for all cases, right? Worst, best, and average cases. And that is the heap sort algorithm. Now let's actually get into the code. All right, so let's get into the code for the heap sort algorithm. First, let me just summarize what we implemented in the last video. So we have here heapify. This is going to take in the array, its size, and the index, which we're going to heapify. Then basically what this is going to do is it's going to choose the largest child, and then it's going to exchange that node with that child. Then we're going to apply heapify again in a recursive manner. Then we have build heap. This is basically going to turn our array into a heap data structure, and we're basically just going to apply heapify a bunch of times. Okay, so now for the actual heap sort algorithm, this is actually pretty easy. It doesn't take a lot of lines of code. First, we need a temporary variable for the exchanges. Then we need to apply build heap here to our array and to the heap size, which is actually just the length of the array. So now that our array is a heap, I'm going to say for int I, and this is going to start out at heap size -1. I is greater than -1 and I minus minus. I'm going to explain this in just a moment. And here we're going to exchange. So I'm going to say temp equals A0. Then A0 is going to be AI. And then AI is going to be the temp, like so. So we've exchanged. So what is this doing? Well, essentially, this is starting out at heap size -1, and it is decreasing. So we're basically starting at the last element of the array, and we're moving to the beginning of the array. Then we are exchanging the root with that element. So the root is always going to be at the index 0. This is a rule. And we're basically exchanging the last element of the heap with the root, like I explained in introduction. So now what we need to do is apply here heapify with the same array, then I, and then 0. So this is going to take in the array. This is the new size of the heap, right? Because we're starting at heap size -1, then we're going to go to heap size -2, heap size -3, and so on. And so I is actually going to contain the new size of the heap, and then 0 is the root, right? So we're actually applying heapify to the root itself, which, like I said, is always at the position 0. And this is actually all we need here for our heap sort algorithm. I'm going to actually apply this right here with the array A and the heap size, like so. And let's see if this works. Let me pull this up. I'm going to run this code. And as you can see, our array is now sorted. In this video, I'm going to talk about linked lists. This is a very important data structure, and in this video, I'm hoping to teach you how and why you should use them, how to insert, delete, and search elements inside of your linked list, and more. So let's get right into it. First of all, why would you use a linked list? Well, up until now, if you wanted to store collections of data or lists of data, you would probably create a vector, right? And this is okay if you're fine with having your data statically allocated and if you know exactly how many elements you want to store in your list. However, if you don't know exactly how many elements you want to store, you would either create a super large array from the get-go, and then the space that you didn't take up would just go to waste. Or if you were adding elements to your vector and you reached its maximum capacity, you would reallocate a larger vector, copy the contents from the previous vector, and keep adding elements, right? Well, you can probably tell why this is not the most efficient way to do this, and that's where linked lists come in. So a linked list is basically a collection of elements which are linked by pointers. So each element in a linked list is going to contain two parts. One is going to be the actual value or the contents of that element, and the other is going to be a pointer that's pointing at the next element in the list. And then the next element is going to have the same thing, right? And then maybe this is the last element, so this is going to point to null, and there we have our linked list. And the first element here is going to have a pointer called head, which is going to be the beginning of the list, right? The head of the list. And this is much better than the options I was talking about before, right? Instead of allocating statically a contiguous block of memory for your vector, you're just going to dynamically on the heap allocate exactly as much memory as you need for each individual element in the list, right? And they can be scattered around your memory. They don't need to be contiguous. So maybe one element is here, maybe one element is here, maybe another one is here. And the most important thing is how you link them together through pointers and not so much where they are located, right? And another great upside is inserting and deleting, especially in the middle of the list, which is something that you can't easily do with a vector, right? So if you want to add an element between these two elements, what do? Well, you allocate memory for that new element, and then you grab its next pointer and you point it at the element that's going to be after it, and then you grab here the pointer of the previous element and you point it at the new element. And there you have it. You've successfully inserted an element to the middle of the list, right? Now you want to delete an element, for example, from the front of the list. Easy peasy. You grab the head, you point it at the second element, and then you delete the first element here. And boom, you've successfully deleted an element from the front of the list really easily, right? Now this does have one downside, which is the search operation. If you want to search for a certain element, you need to do a linear search. There's really no other way. You need to go check each element one by one to see if that element is the element that you want, right? And that's how you search in a linked list. Now, enough with the explanation. I actually want to show you some code because I know that's what you want to see right now. So for this part, I'm going to be using C++. I am going to assume that you're comfortable with the basics of this language. However, it's not going to be something super hard to follow along. So let's get right into it. First of all, each element in our linked list is going to be something called a node. And a node is represented by a struct. So let's type struct here. Let's call this node. And this is going to represent each element of my list. Inside of here, we're going to have two things. We're going to have the actual value of the element, which for simplicity's sake, I'm going to make an integer. And then this is going to be a self-referencing structure, meaning inside of the structure, we're going to have a pointer to another element of the same data type, of this same structure. So we're actually going to have here a node pointer called next. And this is going to point to the next element in our list. So let's actually create our list here. I'm going to call this head. It is going to be a node pointer, and I'm going to allocate this on the heap using new. So I'm going to say new node here, and there we have it. We have the head of our list. Now I'm going to say head value is going to be, for example, 10, and then the head next, since we don't have any more elements, is just going to be null, right? So now we have our list created here, and notice that this is only a representation. So it's not like a vector that you actually look at it and you can see that it is a collection of elements. We're only going to have here a pointer that's going to represent the beginning of our list, and that's going to be our head. Now let's actually create here a function in order to print this list so that we can actually check out what elements we have. This is going to take in our head. And in here, I'm going to teach you how to iterate through the linked list. So in order to do that, I'm going to create here another pointer, which is going to be called current. There's going to be a copy of my head, and I'll actually iterate. So I'm going to say while our current is different than null. So basically, while we haven't reached the end of the list, then I'm going to say that the current equals current next. So I'm basically going to go to the next element of my list. But before that, I need to actually print that element. So I'm going to see out my current value. And let's just get here a separator. And there we go. This is how you iterate through a list. Now let's actually come here. Let's say, oops, not this. Let's say print list, like so, and pass in our head here. And now let me run this. And this is hopefully going to return to us our list, which only has one element for now, which is 10, but let's take care of that now. So I'm probably going to be doing this a lot, right? Because for each element, I'm going to allocate specific memory. So I'm actually going to copy this and delete this. And I'm going to create here a function that's going to automate this for me. So I'm going to say node, which is going to be returned by this function, create new node. I'm going to pass in here the value I want to create the node with, and I'm going to paste this right here. Now, instead of calling this head, I'm going to call this new node, and I'm basically going to do the same thing, but instead of 10, I'm going to say that the value is going to be the value that I pass in, and then all I need to do is return the new node, like so. So down here, I'm going to say node head is equal to create new node with the element 10. And there you have it. Now, if I run this, it's going to output the exact same thing. Now let's actually add a couple of elements to my list. So I'm going to create here a function. This is going to return to us a node pointer, and it's going to be called add to start. This is going to take in our head. This needs to be a pointer, like so. And in here, I'm going to add an element to the start, right? And I'm also going to pass in the value of the new element. So how do I do this? Well, first of all, I'm going to create a node here, which is going to equal create new node. Oops, I need to give it a name first. So let's say new node is equal to create new node with the value that we pass in. So now we have our node, and now let's actually add this to the beginning. But before, I need to make sure that my list is not empty, right? So let me say, if my head is equal to null, then I'm going to say that the head is equal to my new node, right? Because the new node is actually going to be the new head of my list, since we don't have anything there yet. And otherwise, I'm going to add this to the beginning. So I'm going to first say new node next is going to be my head. So the next element after my new node is going to be the current head. And then the head is now going to be the new node, right? So the head is actually going to change. And now all I need to do is return the head, right? And now let me come down here, and I'm going to say that the head is equal to add to start. And I'm going to add, for example, 20. And if I run this, oops, I've forgotten to pass in the head as well in here. Now let's actually run this and see if it works. And there we have it. We've added an element successfully to the beginning of the list. Now let's do this one more time. Let's add to start. Let's pass in here the head, and let's add, for example, 30. And if I run this, we've successfully added 30 to the beginning of the list, right? So easy peasy. Now let's learn how to add an element to the end of the list. So I'm going to create here a new function. This is going to be a void. I'm going to call this add to end. And in here, I'm actually going to pass in a double pointer to head in a value. Why am I passing in a double pointer? Well, that's because instead of returning the new head like I did in the previous function and altering from outside of the function, I actually want to alter the list directly from inside of my function. I don't want to have to do that outside. So for that reason, I'm going to pass in here a double pointer. And then we're going to need to iterate. So as always, let's create here a current copy of my head, like so. And this is double R. And we also need to create our new node. So let's say new node is equal to create new node with the value, like so. And always check if your list is empty first. So let's say if head is equal to null, meaning our list is empty, then my head is going to be my new node, right? And with this, I've actually successfully altered the head from it within our function, right? Because instead of setting the head equal to the return of this function, I've passed in a double pointer, and I've said that the contents of that pointer are going to be the new node, right? And then otherwise, we're going to iterate. So I'm going to say while current next is different from null, then current is equal to current next, like so. And notice that I'm not going until current is equal to no, right? I'm only going until current next is equal to no, because I don't actually want to go to the end of the list, to the part of the list where it is actually null. I only want to go until the last element itself, so that in the end I can say current next, like this, is equal to the new node. And hopefully this is going to work. Let me go down here and I'm going to say add to end. And I'm going to add, for example, 20 here to end, actually 25, so that I have a different element here. And if I run this, let's see what happened here. Oh, of course, I forgot to pass in here the reference to my head. I always forget to do that. So let's run this again. And hopefully now we've added 25 to the end of the list, and we have, right? So let's do this again with another element. For example, 32, something random. And if I run this, now 32 is at the end of my list. Now, probably for the most important part of the whole video, I'm going to teach you how to add an element to the middle of my list. I'm going to use this same approach of altering the list from within my function instead of doing it from the outside. So in order to do that, I'm going to create here a void, let's say add to middle, and this is going to take in a double pointer head, like that. It's going to take in the value of the element after which we want to add the new element and the new value of the new element, right? So like always, we're going to have to create here our new node like this. And this is going to be create new node, and we're going to pass in here the new value like so. And we're also going to iterate. So we need here a current, which is going to be a copy of my head, and I forgot here the equal sign, and there you go. Now, as always, we need to check if our list is empty. So if head is equal to null, then we're going to set the head be the new node, and there we have it. And otherwise, we're going to have to iterate, right? So I'm going to say while our current next is different from null, then current is equal to current next, like that. However, we can't just check if the current next is equal to no. We also have to check if the current value is different from the value that we pass in here, right? Because we are looking for a specific element, right? And once we're done with this, we actually have a couple of options, right? So either we found here the ending of our list, so current next is equal to no. However, we haven't found our element, so current.value is different from our value. Then in this case, this means that the value we were looking for is not inside of our list. So in that case, I'm going to see out element not found and a \n, like that, right? Now, otherwise, if we have reached the end of the list and we found the element that we're looking for, so if this happens, then this is basically the case where we need to add the element to the end, right? So all we need to do is say current next is equal to new node, like that. And otherwise, this means that we found the element we were looking for and it is in the middle of the list, right? So how do we do this? Well, let me actually pull up my whiteboard here. So if we actually analyze here the case where we want to add an element to the middle of the list, for example, we want to add a new element right there, we can't just take the pointer of this element and point it here to the new element, right? Because then this part of the list is just going to be lost. We're going to have a memory leak because we don't really have anything pointing at that piece of the linked list anymore, right? So we don't really know where it is. So let me actually delete this, not the pointers. And before we actually do this, we need to point the next pointer of the new element to the next element, and then we can point this to the new element, right? So if I actually go here to my code again, so what do we have to do? First, we have to say that the new node next is going to be the current next, so the next element after current, And then we can say that the current next is equal to new node, right? So first we link the element that's after current to the new node, and then we link current to the new node. And that is all we need for our add to middle function. Hopefully this is going to work. Let me say here, add not to end to middle, like that. And we're going to pass in here the reference to our head. The value can be, for example, 10, that's right in the middle. And then the new value is going to be, for example, 23. And now let's actually run this to see if it works. And there you go. Now 23 is after 10 here. Now let's actually add this to the end of the list to see if our function is covering all the cases. And there you go. And now let's add it after an element that doesn't exist, for example, 90. And if I run this is going to give me element not found, and then the list is going to be intact. Perfect. So that is our add to middle function. Now let's learn to actually remove an element from my list. And I'm actually going to do this with only one function. Instead of having a function to remove from the beginning, the middle, and then the end, I'm going to cover all of the cases in one go. So let's get into it. So for this function, I'm actually going to make this return a node pointer, which is going to be the new head. Let's call this remove. This is going to take in our current head and the value of the element we want to remove. So first of all, let's make our copies. Let's say current is equal to head. And we actually need a pref pointer, which is going to point to the previous element. I'm going to explain better what that means exactly. And now we're going to have a couple of cases. Always check if your list is empty. So if our head is null, we're just going to return null because we don't have anything. Otherwise, if our head value is equal to the value of the element we're looking for, then that means that we're looking at the element that we want to remove. Now, how are we going to do this? Well, first of all, we're going to say that the head, or rather, we're going to say that current, which is the copy of our head, is going to be our head next. So it's going to be the value after our head. And then we need to delete our head, right? So we need to basically free the memory that we allocated for our head because we're not going to need it anymore. And we're just going to return current, which is going to be the new head of our list, right? So that's how you remove an element from the beginning. Now, otherwise, we're going to iterate it. So I'm going to say while current next is different from null, and we haven't reached the value that we want. So current value is different from the value we're looking for. Then we're going to set the current to be current next. So we're going to keep going in our list. However, we're also going to store the previous element. So I'm going to say pref equals current. So we're going to store current and we're going to move on to the next element. You're going to see why this is important. Now, when we're done iterating, we're going to have a couple of cases. So if our current next is equal to null, so if we've reached the end of the list, however, if our value is not the value that we want, then that means that we've reached the end of the list and we haven't found the value that we want. So we're just going to return head, right? We're not going to remove anything. We're just going to return the head, which remains unchanged. Else if the current next is equal to null. So if we've reached the end of our list, but the value that we actually wanted to reach is there, so we have the element that we wanted at the end of the list, then we're going to do a couple of things. We're going to say that the pref next, like that, is going to be equal to null. So the element before the last element is going to point to null, and then we need to delete current, right? So we're going to basically free up the memory that current took up, right? And otherwise, then that means that the element that we want to remove is at the middle of our list. So what we're going to do, well, we're going to say that the pref next, like this, is equal to current next, like so. And we're going to delete current, right? So we're actually going to link the previous element to the element after it. And then we're going to free the memory corresponding to current, right? Let me actually open here my whiteboard. So if you have here a list with a couple of elements and you want to remove this element right here, you need to take the pointer from the previous element and point it at the next element, and then you need to remove that element, right? So that's exactly what I did. I took the previous element, I've made its pointer point at the element after the one I want to remove, and then I've deleted the one I want to remove, right? And then all I need to do is return the head that remains unchanged, right? And this is how you remove an element from any position in your list. Now let's actually see how this works. Guys, I apologize, but I've actually made a typo here. This is not one equal sign, this is two equal signs. And now this should work because it wasn't working before. So let me say remove here head, and let's remove, for example, 30, which is the first element in our list. And if I run this, there you go. So now it's working. We've removed the first element of our list. Let's remove 32, which is the last one, to check all of the cases. There you go, 32 is gone. Let's remove now 10, which is exactly in the middle, and there you go, 10 is now gone. And just for the sake of it, let's remove 25 to make sure I haven't made any more mistakes, and there you go, now 25 is gone. So a hash table is basically an array that has a hash function. How does this work? Well, we're going to have here an array, like I said, that's going to have different indexes, and this is going to be our hash table. Now, if you want to insert an element in this hash table, all you need to do is get a key that's going to represent the element that you want to insert, apply a hash function to that key, and that hash function is going to map to an index of the array where you're going to put that element. So for example, if your key is a string, for example, a name, you apply a hash function to it that turns it into a number, which is going to be the index of our table, and then you put the element in that index. So that is how a hash table works. Now, obviously, this is a great advancement in relation to arrays and linked lists, because any operation that you want to perform, whether it is inserting, searching, or deleting elements from the hash table, can be done in constant time or really close to constant time. So O of 1, right? Now, this hash function needs to be computationally light, so it doesn't really matter if you have a hash table, if then the hash function is not fast and it is really computationally dense and you need to waste a lot of time to apply it, because then it really defeats the purpose of a hash table, which is speeding up the process of searching and inserting elements. The second thing is it should always produce the same output. It doesn't matter if you have a super fast hash function, if then each time you calculate it, it gives you a different index of the array. And the third thing is you want it to be pretty random, right? You want the values to be spread out throughout the table, and you don't want different values or different keys to map to the same location, because then you're going to have collisions, and dealing with that is not the best. Now, keep in mind that a hash table also has disadvantages, right? It doesn't support operations like sorting, and you're probably going to have to allocate more memory than necessary. So you're going to waste a lot of memory as well. Now let's actually get into some code, enough with the theory, because I know that's what you really want to see. All right, so let's do this. My hash table is going to be made up of structs. I'm going to name this car, and each car is going to have a license plate, which is going to be a string. As of now, that's all I'm going to put in here, but I am going to add something in the future. Now, let's actually create here our hash table. This is going to be an array of car pointers, and the size is going to be num cars, which I haven't defined yet. And I'm going to initialize everything at null. All right, so now let's define up here num cars, like that. And this is going to be 10. All right, so now we have our hash table created. How do we actually hash each plate to a value? So let's actually create here a function called hash func, and this is going to take in our license plate. So string plate, like that. And we need a couple of values here. First, we need our hash value, which is going to be started at 0, and it's going to store the actual hash for our plate. And then we need the length here of our plate, so plate dot length, like so. And now I'm going to iterate through my plate. So for int I equals 0, I is smaller than the length, I plus plus. And now I'm going to say hash value plus equals int the plate at position I. So we're basically going to add each character, or the ASCII value of each character of my plate, to the hash value. And I actually don't know if you need this int function right here, but anyways. So now let's say hash value is equal to the hash value itself times the plate I, like so. Now let me actually encapsulate this in that function. It's going to be int, and we don't need the space, and we don't need the space. All right. Now in the end, let's actually return here the hash value. However, there is a slight problem with this. Let me actually illustrate that. So I'm going to create a car here called car1. Let's say car1.plate is equal to AA00AA. Now let's say int result is equal to the hash func of car1.plate, like that. And let's see out here result, like so. So if I actually run here this code, this is going to output this huge number. Now, obviously, this is not a valid index of our table. So how do we make this huge number fall between 0 and 9, right, which are the possible positions of our table? So that is actually really easy. All we have to do is go here and calculate the remainder of this by the number of cars. Let me actually put parentheses right there. And there you go. Now this hopefully will fall between 0 and 9, and there you go. Now we get 5, right? That is a valid index of our table. So all you need to do is really calculate the remainder of the division by 10, right? Because the remainders of the division by 10 can only be the numbers 0 through 9, right? There's no really other possibility. All right, so this is going to be our hash function. Now keep in mind that this is a very simple hash function. There are a bunch of hash functions out there. There is city hash, there is murmur hash, there is farm hash. So all of those are nice hash functions that you could explore, but this is a simple one that we'll do just for now. Now let's actually add cars to our table. Let me delete this. And I'm going to create here a void function called insert. This is going to take in here our cars hash table. And it's also going to take in a pointer to a car. So in here, the first thing is calculate the hash value of this car. So this is going to be hash func, the car plate, like that. And now let's actually insert. Well, to do that, all we need to do is the cars at the hash value, which is going to be our index, is going to be the car that we pass in, like that. And that is all we need to do to add a car to our table. So let's insert here with our cars list, and let's insert car1. And I actually need to pass in a reference here because my function is asking for a pointer. And now let's code a function that allows us to see our cars. Let's say print table, like that. This is going to take in here our cars table, like so. And now let's iterate. For int I equals 0, I is smaller than num cars, like so, I++. And now I'm going to code here something that allows us to see whether a position of the table is empty or not. So let's say if cars at index I is null, then I'm going to see out null in a string and a \n. And otherwise, I'm going to see out cars I plate, and I need to actually see out this. So let me say see out here the cars I dot plate, and then I'm going to do the same thing with a \n. So this should probably allow us to see our table. Let's print the table with the cars. Now let me actually run this, and let me pull this up to see what we get. And there we have it. Now we have here our hash table. It's going to have a null in the positions that don't have anything, and then it's going to have the car that we just added. So let's add here a couple more cars. Let me say here, let me paste that in. Let me say here car2. Let's give it another license plate, 90 and 1P, something random. And let's print our table. All right, perfect. Now let's grab here this again, and let me paste it. And now let's name this car3, and let me see if I can do this. So B00AA, like that. And let's run this now. All right, so that did exactly what I wanted it to do, which is these cars, AA00AA and BB00AA, are going to map to the same location. Now, since we don't have anything that allows us to deal with collisions, when we add the second car to that index, it's just going to override the previous car that was there before, right? We don't really want that to happen. So what are a couple of solutions that we can have? Let me grab here my whiteboard and let me grab my pen. So how do we deal with this? So the first solution is something called linear probing. So imagine that we have our table right here. We have a bunch of indexes. Now imagine that this index is taken and we add another value here to this index. This is obviously going to result in a collision, so we do linear probing. We go look for an empty position. So we go to the next position. If it is not empty, we go to the next position. If it is not empty, we go to the next, and so on. And maybe this is empty, so we put our element right there. Now, this obviously is not the best way to deal with collisions, right? Because this actually defeats the purpose of a hash table, which is not having to waste time inserting and looking for elements. We don't want to look for an empty slot every time we want to add an element, right? And also, if we have our table full, we either have to reallocate a new table or we just can't add any more elements, right? So the second solution here is going to be double hashing. So we have a first hashing function, and this is going to generate a collision. And so what we do is we apply a second hashing function to determine the increment. And then this is going to give us our index. Now, this is also not the best way to do this. And so the way I'm actually going to teach you is going to be external chaining. Let me write that here. And with external chaining, each position of our table, instead of being just a pointer, is going to be a linked list. Now, if you don't know what a linked list is, I do have a video on that. It is pretty complete, and it's going to give you the beginner tools to understand this. But basically, if we have here our hash table, it has a bunch of indexes, and each position is going to be the head of a linked list. And then when you want to add an element and you have a collision, you just add that to the linked list. And then you add that to the linked list, and so on, right? So each position is going to be a linked list, and all you need to do is chain the elements together. So let's actually see how this works here in our code. So the first thing I need to do is add here in my car a next pointer. So I'm going to say car next, and this is going to contain the next element of our linked list, right? Now I need to alter here my insert function. I need to calculate the hash value in the same way, but now we're going to have a linked list in the position of the hash value. So what do we need to do? We're going to say car next is going to be cars at the hash value, like so, because the cars at hash value is going to be the head of our list, and we want to add the car. We want to basically make the new car the new head of our list, and then we have to say cars at hash value is going to be car, like so. And this is going to add our car to the beginning of our linked list, so to the head of our linked list. And now we also need to alter here the print table function. So instead of this, I'm going to say car pointer is going to be current, like so. And this is going to be the cars at the index I. And now let me say while current is different from null, I'm going to see out here current plate. And I also need here a separator so that we don't have everything smushed together. And then I'm going to say current is equal to current next, like that. And now down here, I'm going to say cout a \n, like so. So let's actually see if this works now with those same plates that we had before. So if I run this now, this is going to output our table. And as you can see, in the position where we had a collision, it's going to give us a linked list. And let me do this again. So let me find here another car with collisions. I'm going to name this car 4, like so. And instead of BB, I'm going to say CC. And if I run this now, there you go. Now we had another collision, and that new car that we added is at the beginning of the list. So that is how you do external chaining. Now let's learn how to remove an element from the table using external chaining. So I'm going to go up here. I'm going to say void remove, and this is going to take in here our cars list and the plate of the car we want to remove. So the first thing, as always, is to get the hash of the plate. So let me say hash func with the plate. And then keep in mind that each position of my table is going to be a linked list. So I'm going to say car current is going to be the cars list at the hash value, like so. And this is going to be a linked list. And also I need a pref because we're going to remove, and we're just going to set this equal to current in the beginning. So now we need to iterate through our linked list. I'm going to say while current is different than no, and then we need to check if we found the car that we want. If current plate is equal to the plate that we pass in, and in here we're going to have a couple of cases. So if our hash, if our cars at the hash value is equal to current, this means that the car that we want is at the head of our list. So we're going to basically eliminate the first element. And how do we do that? We're going to say cars at the hash value is equal to cars at the hash value next, right? And this is how you remove an element from the beginning. And otherwise, this means that the element that we want is either at the end of the list or in the middle of the list. So all we need to do is say pref next is equal to current next, like so. So we're basically going to link the previous element to the element that's after the element that we want to remove. And then the element that we want to remove is no longer going to be linked to the other elements, right? And then in the end, all we need to do is say pref equals current, and current is equal to current next, like so. And also, if we find the car that we want, I'm going to return. So we're going to terminate the function. And down here, I'm going to say cout not found. So if we haven't found the car that we want, we're going to just, print a flag to say that. Okay, so now let's actually remove here an element. So let me say remove. This is going to take in the cars list, and then it's going to take in a string. Let's say, for example, BB00 and AA. All right, and if I run this now, let's see what it outputs. And there we go. Now we have removed that car from our list. Now let's do the same thing here with this car. And if I run this now, there we go. Now we've removed that car from our list. And that is all we needed to do. Sorry, I keep saying list, but I meant hash table. Now, this is actually very similar to a search function, to how you would do a search function. I'm actually going to grab this here, and I'm going to say, instead of remove, search, like that. And this is going to this is going to return to us a car pointer, like that. And now, instead of deleting the element, I'm going to return the current, like that. So I'm basically going to return the car that we want. And down here, I'm going to return null. So this is going to find the element that we want. So let me go down here. Let me say car, and it's going to be car, and it's going to be search. And let's, for example, search for AA00AA. And let me just print here found so that we can actually see that we found it. Found. Exclamation point. And now let me run this and let me pull this up, and it's going to say found because we found the car that we wanted, and it's going to print our table. So that is actually all I wanted to show you today. That is how you insert, delete, and search for elements in a hash table. That is how you create a hash table with pointers to structs, and that is basically it. In this video, I'm going to talk about binary search trees. So first of all, what is a tree? So a tree is made up of nodes that can be connected into branches. So for example, this is a tree. This is also going to be a tree with only one branch. And this is also a tree, right? So all of these are going to be trees. Now today I'm going to talk about a very special type of trees, which are binary search trees. Now these trees are called binary because every node or every element of the tree can have at most 2 children. So if you look here at the root, which is basically the top node of the tree, it only has 2 children, right? Left and right. Now, if you look here at 45, for example, it only has 1 child here, 40. And if you look at 18, 23, 2, and 9, these are going to be leaves because they have 0 children, all right? So that's why this tree is called binary. Now, it is also called a search tree because it has a very important property. If you look closely here at the root once again, and you look to the left, you can see that its left child is smaller than the root. and the right child is going to be greater than the root. And this is true for every node of our tree. And essentially what this means is that the whole left subtree of my root is going to have elements that are only smaller than the root, and the whole right subtree is going to have elements that are greater than the root. And this, like I said, is true for every element of the tree. And this really facilitates the process of searching for elements in our tree. So for example, if you want to search for the element 9, how do we do that? Well, we're going to start here at the root. Now 9 is smaller than 20, right? So we know that the whole right subtree can be eliminated, right? Because all of these elements are going to be greater than the root. So we go to the left here. Now 12 is greater than 9, so we go to the left again. And now 8 is smaller than 9, so we go to the right and we have found our element, right? So that is how you search for elements in the tree. And as you can see, this is a very efficient way to do this. Now, in order to insert an element into the tree, it is the same process, right? So for example, we want to insert 22 here in the tree. This is always going to be inserted here at the bottom of the tree, right? So how do we do this? Well, we start at the root. The root is 20. It is smaller than 22. And so we go to the right, right? Because 22 is going to be greater. It has to be at the right of the root. Now for 32, 32 is greater. So we go here to the left. And now 23 is also greater. So we're going to put 22 here at the left of 23. And we have successfully inserted 22 onto our tree. Now, in order to remove here an element, it is a little bit more complicated. And we're essentially going to have 3 possibilities here. So either the node we want to remove is going to be a leaf, so it doesn't have any children. So for example, if we want to remove 2, it doesn't have any children. All we have to do is grab it and remove it from the tree, right? Really easy. Now the second option is the node we want to remove has 1 child. For example, if we take here 45, how do we remove 45? Well, that's really easy. We grab the child, we exchange it with the node we want to remove. So 40 goes here, 45 goes here. And then we grab the node we want to remove and we just remove it. And there we go, we have removed 45. Now the third option, our node is going to have 2 children. So this is going to be a little bit more complicated. So for example, how do we remove here 32 from our tree? Well, we're going to grab the left subtree here of 32. And we're going to find the greatest element in the left subtree. That is going to be 23. So we're going to grab 23 and we're going to exchange those two. So 32 goes here, 23 goes here. And now, as you can see, this is one of the previous cases that we've talked about, right? Leaf, or it has 1 child. Now, in this case, it has 1 child. So how do we remove an element with 1 child? We grab the child, we put it in the place of the element we want to remove, and then we remove the element. And this is how we remove an element with 2 children. So now I'm going to talk about traversal. So traversal is essentially going through every node of the tree in a certain order. And there are 3 ways we can do this. We can do this pre-order, in order, or post-order. So let's start here with pre-order. So pre means before, right? So essentially what this means is for every node of a certain subtree, we're going to visit first that node before we visit its children. So the order here is going to be the root of the subtree, then we're going to visit its left child, and then we're going to visit its right child, right? So what will this look like? So first we're going to go to the root. So we're going to visit the root first. I'm going to write here 20. Then we're going to go to the left side. Now 12 is going to be the new root of a new subtree. So we're going to visit the root first, and then we're going to visit the left side. Now 8 is a new root. We're going to write 8 right there. And then 2 is the new root now because we went to the left. Now 2 doesn't have any children, so we go back up to 8. So 8 is the root of the subtree. We've already gone to the root itself, we've already gone left, and now we're going to go right, which is 9, right? So now we have visited this whole subtree, so we're going to go back to 12. Now we have this subtree, we've already gone left, we've already gone to the root, and it's time we go right to 18, right? So we go to 18 here, and then we're going to go to the root again, and we have already visited the left side, we've already visited the root itself, so we go to the right. Now 32 is the new root of this subtree, so we're going to visit 32 first. Then we're going to go to the left of 32, which is 23. It doesn't have any children, so we just write 23, and then we go to the right of 32, which is 45, right? So this is going to be the pre-order traversal. So first we're going to go to the root, then we're going to visit the left subtree, then we're going to visit the right subtree. Now, in order, first we're going to visit the left child, then we're going to visit the root itself, and then we're going to visit the right child. And you will see in just a moment why this is called in order. So first we go to 20, and the first thing we do when we get to the root of a new subtree is visit its left child. We go to the left again here, and we go to the left. We can't really go to the left anymore, so we visit the root, which is 2. We can't really go to the right, so we go back up to 8. Now for this subtree, we have already visited the left, so we go to the root itself, which is going to be 8, and then we go to 9, which is right. And we're going to go back up to this subtree where 12 is the root. We have already gone to the left, so we go to the root itself, and then we go to the right, which is 18. Now we go back up to the main root, which is 20. We have already visited the left subtree. We visit the root itself, and then we visit the right. Now here we're going to visit first the left, so we're going to go to 23. Then we're going to go to the root itself, which is 32. And then we're going to go to the right child, or the right subtree, which is 45, right? And as you can see, this is going to give us the elements in a sorted manner. If you do this in the other way around, so in the other direction, you're going to get a descending order. Like this, we got an ascending order, and this is why it's called in order. Now for the last one, post order is called post because the root is the last thing we're going to visit. So first left, right, and then the root. Right, so we're going to start here at 20, we go to the left, we go to the left, we go to the left, and here before we go to the root, which is 2, we go to the right. Now there's nothing to the right, so we just go to the root itself. Now we go back up to 8, we went to the left already, now we need to go to the right, which is 9, and then we go to the root itself, which is 8. Then we go back up to 12, we have gone to the left, then we need to go to the right, which is 18, and then we go to the root itself, which is 12. Then we're going to go to 20 again. We have already visited the left side, so we go to the right. Now for 32, first we need to go to the left, which is 23. Then we go to the right, which is 45, and then we go to 32 itself. And now for the last element here, it's going to be 20, the main root here of our tree. So this is how you traverse a tree. So essentially how you go through every node of the tree in these 3 different ways. Now the last thing I want to talk about is going to be time complexity. So on average, searching in a tree is going to take log of n time, in which n is the number of elements in the tree. And the reason for this is that every time we go to a new branch of the tree, we're essentially eliminating half of the tree. And this is going to result in a log of n time, right? Log of base 2. However, in the worst case, we're actually going to end up with an O of n. Why? Well, let me give you an example of a tree that looks like this, right? We only have one branch, and we have here n elements. If we want to search here for the last element of the tree, we're going to have to go through every single element of the tree before we find it. So for that reason, we're going to have, in the worst case, a time complexity of O of n for searching in a binary search tree. The first thing I'm going to do here is create a struct, which is going to be representing the elements of my tree. I'm going to call this node, and in here, I'm going to put a couple of things. First, we're going to have the value itself of the element. I'm going to make this an integer for simplicity's sake. And then we're going to have 2 pointers of the type node. So essentially the node inside is going to have 2 pointers to another element of the struct node of the type node, and these are going to represent the children of this node. So we have a left child and a right child. Now let's actually insert some elements here onto our tree. So first of all, let me create here an insert function. This is going to return to us a node, and it's going to take in the value here, and it's also going to take in the root here of my tree. So the root is essentially the top element of the tree, right? Now I am going to be allocating memory for new nodes, and I am going to be creating new nodes inside of this function. So I'm actually going to create here a function in order to do that. This is going to return a node as well. Let's call this create new node, and it's going to take in the value of the new node. So I'm going to create here a new node variable. And like I said, I'm going to allocate this on the heap. So I'm going to use new node like so. And now let's just initialize here the values. So let's say that the value is equal to the value that I pass into my function. My left child in the beginning is going to be null because it doesn't really have any children, and the same for the right. So this is going to equal null. And then all I have to do is return the new node like so. So this is going to be our create new node function. It's going to take in a value, allocate memory for a new node, initialize its values, and then return it. And now in my insert function, I'm going to have a couple of cases. I'm going to say if the root is equal to null, then that means that our element doesn't have, our tree doesn't have any elements, or we've reached the end of a branch and we just need to add the node right there. So here I'm going to return create new node with the value like so. So essentially this is going to put this node in that position. Okay. Now, if the value that I pass in here is smaller than the root dot value like so, then that means that we need to insert this node to the left of the root, right? To the left subtree of the root. So in this case, I'm going to say that the root left, so the left child of the root, is going to equal, and I'm going to recall insert with the same value, but this time I'm going to pass in the root left, right? Because I need to put the element at the left of the root. Right? And otherwise, that means I need to put the element at the right of the root because it is greater than the root itself. So I'm going to say that the root dot right is equal to insert. And in here, I'm going to pass in the same value. And now I'm going to say root right like so. So let's go over this one more time. So if our root is null, it means that we don't have any elements or we've reached the end of a branch. It means we're going to put the element in that position. So I just need to return a create new node, which is going to return to us the new node that we just created, right? Now, if the value of my new node is smaller than the value of the root, then that means I need to put it at the left of the root. So I'm essentially going to recall insert in a recursive manner with the same value, but this time I'm going to insert it at the left of the root. So I'm going to put it at the left subtree. And otherwise, it means that the value is greater than the root. So I'm going to say that the right child of the root is going to equal insert the same value, but at the right side of the root. All right, that's all this does. And I'm actually going to turn this into an else if. Now, in the end, I'm just going to return here the root. Okay, so this is going to be our insert function. Now, how do we actually do this? Well, first of all, we need here a node. This is going to be called root, and this is going to represent the beginning of our tree, right? So this is going to be the root of our tree. And essentially, the way we use the insert function is we're going to say that the new root is going to equal whatever is returned to us by the insert function. So for example, let's insert 10. Let's pass in here the root. And this is going to create basically a tree with the element 10. And we can do this a couple of times, give it a few values. All right, so now that we've inserted a couple of elements onto our tree, let's create here a way for us to see the elements of our tree. So I'm going to create a void here called traverse. And with this, we're going to essentially traverse our tree. So essentially go through every node of the tree in a certain order. And in here, I'm going to do in order traversal, meaning we're going to get the elements sorted by increasing order. So how do we do this? Well, first of all, if the root is equal to null, then we're just going to terminate our function. So I'm going to return. Now, otherwise, in order is essentially we're going to go to the left child, then we're going to go to the root itself, and then we're going to go to the right child. So we're going to first traverse here the root left, like so. Then when we're done, we're going to see out the root value and a \n like so that we can actually see. And then we're going to go to the right side or to the right subtree of the root. So traverse right. Okay, now let's actually see if this works. I'm going to say here traverse our root like so. And let me pull this up. Let's see if this works. I forgot to initialize here my root at null like so. All right, so let's try this again, see if it works. All right, perfect. And as you can see, we have gotten the elements in a sorted manner. So everything is working correctly. Now let's make here a search function. This is essentially going to be the same as insert, but instead of insert here, I'm going to call this search. And the way we're going to do this is, if the root is equal to null, then that means that we've reached the end of the tree and we haven't really found our element. So we're just going to return here null. Now, if the root value is equal to the value that we pass in the value we're searching, then we're going to return the root, right? Because if the values are equal, that means we have found the element we want. Now, else if the root value is essentially greater than the value, we're going to have to search in the right side of the tree, right? So we're going to return search root right, like so. Or sorry, we're going to search in the left side of the tree. I apologize. So this is not right. This is going to be left, right? Because if the value is smaller, then it needs to be to the left of the root and not to the right. Okay, I apologize. And otherwise, that means that the value is going to be greater than the root. So then we're going to have to search at the right. Okay, so we're going to return here. This is a return statement like so. Search to the right side. And this is essentially going to be our search function. Let's see if this works. I'm going to see out here search, and let's search, for example, for 2. I'm going to pass in the root as well, and let's see out the value here to see if we have actually found 2 or not. And there you go. Now this outputted everything smushed together because I didn't add an end line, but essentially 2 is here and we have found it, and that is what matters. So let me comment this out, and that is the search function. Now the last function we need is going to be the remove function. However, before that, I want to create 2 very simple functions to find the maximum and the minimum values of the tree. So both of these are going to return nodes. The first one is going to be called max, and it's only going to take in here the root. So essentially, to find the maximum element in the tree, all we need to do is go right? Because if we go right enough times until we reach essentially the end of the branch, we're going to find the greatest node. That's literally the definition of binary search trees, and that's the property that make them a binary search tree, right? So I'm going to say, if the root dot right is different from null, then we're going to return the max, but instead of passing in the root, we're going to pass in the root right, like so, right? So if the root dot right is not null, then we're going to go to the right. We're going to keep going to the right. Now, otherwise, we're going to essentially return the root, right? Because if the root at the right, if essentially the right child of the root is null, then that means that that is the last child to the right, if that makes sense. So we're just going to return it because it's going to be the maximum value. I don't know if that makes sense. I hope it did. And the same thing for minimum. I'm going to grab this. I'm going to change this to min. And now everywhere that says right, I'm going to change to left, right? Because if we go left all the time, that means we're going to find eventually the minimum element. So those are really easy functions. And now let's actually implement the remove, which is a little bit more complicated. This is going to return to us the element that we're removing, and it's going to take in the value of the element we want to remove, and of course the root, like so. Now for the remove function, we're going to have to search first for the element we're looking for. So I'm going to say here, if the root is equal to null, essentially we haven't really found the element we wanted, it doesn't exist, so we're just going to return null. Now else if the value of the element we want is smaller than the value of the root, then we're just going to say that the root left, right, because the value is smaller, is going to be equal to the remove function again with the value, but this time we're going to pass in the root left, like so. So essentially, if the value is smaller, we look to the left, and if the value is greater, we look to the right. So root right is equal to remove, and in here I'm going to pass in the value and the root right, like so. So now that we have found our element, I'm going to say else. So essentially, if the value is equal to the value left, right, we're going to do a couple of things. First, I'm going to create here an auxiliary variable. And what is this telling me here? Okay, so I added 2 else statements. So let's make this an else if statement. So let's say value is greater than root value, and this should work now. All right, so first we have an auxiliary variable. Now I'm going to say if the root at the left is not equal to null, so essentially if we have a left child, and if the root to the right is not equal to null, so essentially if the node that we want to remove has both a right and a left child, it has two children, then we're going to have one case. Now, otherwise, that means that either the node has one child or it doesn't really have any children. So this case is easy. I'm going to say that the auxiliary variable is going to be the root. I'm going to say if the root left is equal to null, so essentially if it has a if it doesn't have a left child and the root right is equal to null, so if it doesn't have, if the element we want to remove doesn't have any children, all we need to do is say that the root is equal to null. So essentially we just say that our element is equal to null. Essentially we just remove it. Now else if the root left is equal to null, so essentially if we have a right child, then I'm going to say that the root is equal to root right? Because if the element only has one child, essentially we exchange the child with that element. And otherwise, I'm going to say that the root, oops, I don't need these curly braces. I'm going to say that the root is going to be equal to root dot left, like so. So we've essentially removed the right child, okay? And now in the end, all I need to do is say, with a tab here, delete our aux, right? So let's go over this one more time. I said that my auxiliary variable is going to be the root. Now, if the root left is equal to null and the root right is equal to null, our root doesn't have any children. All we need to do is set it to null and we've removed it. Now, otherwise, if it has a right child, then our root is going to equal that child. And if it has a left child, then our root is going to equal that child. And then all we need to do is delete the root. So essentially remove it from the memory. Now let's do the other case where our variable, or sorry, our element has two children. This is a little bit more confusing, but we can do it. So the first thing we're going to do is say that the aux is going to be equal to the maximum. And if you remember, in this case, we need to find the maximum element to the left of the element we want to remove. So I'm going to pass in here the root left. So now our aux is going to be the maximum element to the left. Then I'm going to say that the root value is going to be the value of aux, right? So I'm essentially going to exchange the value of the element we want to remove, which is the root, with the value of the maximum of the root to the left, if that makes sense. And then I'm going to say that the aux value is going to be the value of the element we want to remove, right? So essentially we're exchanging the values of the root and the auxiliary variable, which is the maximum of, well, the left subtree of the root. Sorry if this is confusing. And then I'm going to say that the root left is going to remove, essentially I'm going to pass in the same value, but in this case I'm going to pass in here the root left. So again, let's go over this one more time. So if the element we want to remove, which is our root, has both a right and a left child, we're going to have to exchange the element of the root with the largest element to the left of the root. So essentially we say that the auxiliary variable is going to be the maximum element to the left of the root, and then we're going to exchange the values of those elements, right? So the value of the root is going to be the value of the greatest element to its left, and the value of the greatest element to its left is going to be the value of the root. Then all we need to do is say that the root left, so essentially the left subtree of the root, is going to equal remove that same value but from the left of the root. And this is going to fall in one of these cases where essentially our the element that we want to remove has one child or 0 children, okay? So I hope that makes sense. Now in the end, down here, all I'm going to do is return the root. Oof, okay, so that is it for the remove function. Let's actually see if this works. So I'm going to say here that the root is going to equal remove, and let's remove, for example, 22. Let's pass in our root as well, and then we're going to traverse the tree. So I'm going to run this code and let's see if 22 is there. It is actually not, so that means that we have successfully removed it from the tree. Let's try another element, for example, 15. Now 15 is not in there. 10, Now 10 is not in there, 6 for example, and you get the idea. Oops, let me run this again. All right, you get the idea. So that is the remove function. In this video, I'm going to talk about the queue data structure. So this is a data structure that follows an idea called FIFO, and this stands for first in, first out. And it essentially means that the first element that you add into the queue is going to be the first element that you're going to remove or process. So let me give you a real life example here of a line to the movies. When someone arrives, they go to the back of the queue, right? To the back of the line. And when a person is done buying their tickets, they're going to go away, right? They're going to be removed from the queue. Now, a queue data structure is the exact same thing. You can only really add people to the end of the line or to the end of the queue, and you can only remove people from the front of the queue. And this is how a queue data structure works. Now, how do we actually implement this? Well, we can implement this using a linked list. However, I'm going to be using an array just because it's a little bit simpler and you don't really have to have any prior knowledge. So this array is going to represent our queue. Now, how do we actually implement this behavior? Well, we're going to have two variables, a front, which is going to be the front of the queue, and a back, which is going to be the back of the queue, right? The front is going to start out at the first position. The back is going to start out at outside of the queue, right? So if you want to add an element, you're going to add to the back, right? So you add an element here, for example, you grab the back and you move it over, right? You want to add an element here, you grab the back, you move it over, and you can't really do this to the front of the queue. So for example, if you want to add all of these elements, now the back is going to be right there, right? And this is how you add elements to the queue. Now, if you want to remove an element from the queue, you just grab the front and you move it over. You don't really need to do anything to this element because the queue only really exists between the front and the back, right? So these elements in here and here are not really going to be inside of the queue. And for that reason, you don't actually need to remove this element from memory. You just leave it there, but it is no longer in the queue, right? Now, how do you know if your queue is empty? So imagine that you have this disposition. For example, the front is here and the back is here. You're going to remove this element, right? So you grab the front, you move it over, and now only this element is inside of the queue. And we're going to also remove it. So we grab here the front and we're going to move it over. And now our front has surpassed our back, right? Our front is actually in front of the back. That doesn't really make sense. And so when this happens, we know that the queue is empty, right? Because it doesn't really make sense. So this is the verification you have to do in order to see if the queue is empty or not. Now consider this disposition. We're only going to have one element at the back of the queue, and both my back and my front are going to be pointing at that position. What happens when I want to remove this element? Well, I grab my front and I'm going to move it over, right? However, this position is not a valid position of the array. So what do I do in this case? Well, that's totally fine. I just grab the front and I move it here to the beginning of the queue, right? So now I have essentially removed this element, and instead of going outside of the bounds of the array, I went back to the beginning. So this means that the queue is going to be a circular data structure, right? When you don't really have any more valid indexes, you just go back to the beginning. All right, so that is the implementation of the queue. Now let's actually write this in code. All right, so let's get right into it. I'm going to represent my queue with a struct like so. In here, we're going to have a couple of attributes. First, we're going to have the front of the queue, the rear or the back of the queue, and then we're going to have a capacity, which is essentially going to be the size of the array, which is going to represent our queue. And then we're going to have the queue itself, which is going to be an array of integers. All right, so first of all, let's define here a constructor. This is going to take in a number c or an integer c. And in here, we're going to define everything. So first of all, the front is going to be 0. The rear is going to start out at -1, so out of the bounds of the queue. And the capacity is going to be this c that we pass in here. And then the queue itself is going to be an array allocated on the heap with the size c that we pass into our constructor. All right. Then, since we're allocating this on the heap, we can also have here a destructor queue, like so. And in here, we're just going to essentially delete the queue from memory. Oops, not like this, like that. All right, if you don't understand what this means, don't worry, this is not really important. It just basically takes your queue and deletes it from memory since we're allocating it on the heap. All right, then we're going to have a couple of methods. First, we're going to start with the boolean is empty. This is going to check if our queue is empty or not. And in order to do this, I'm just going to return here the front is bigger than the rear, right? Because if the front surpasses the back of the queue, that means that the queue doesn't really have any elements inside. All right, now we're going to get to the methods that actually are important. So first of all, we're going to have here an in queue. So in queuing means adding an element into the queue. This is going to take in a value, the new value that we're going to put inside of the queue. And first of all, we need to check if the rear is equal to capacity minus 1. Then that means that the queue is going to be full, right? Because as I said, you can only put the capacity minus 1 elements inside of the queue. So in this case, I'm going to see out here first a \n, and then queue is full like that, then another \n, and I'm just going to return like so. So if the queue is full, I'm not really going to do anything. If it's not, I'm going to say queue plus rear is going to be equal to the value like so. So essentially, I'm going to increment my rear, my back of the queue, and I'm going to insert the value there because I can only really put elements in the back of my queue, right? So I hope that was easy to understand. Now let's get into the dequeue like so. This is going to remove an element from the queue. That's called dequeuing, right? And the first thing we're going to check here is if this dot, and let me check here, is empty. So if the queue is empty, it doesn't really make sense to remove an element from the queue. So I'm going to see out \n, queue is empty, !, \n like so. And I'm going to return -1 just as a code to tell me that nothing really happened, right? And otherwise, let's actually do the dequeue process. I'm going to create here a value. This is going to be the queue front, essentially the value we're going to remove, right? Because we can only remove elements from the front of the queue. And the reason why I'm doing this is because usually when you remove something from the queue, you return that value, just like a pop method, like a normal pop method would. Then I'm going to say the front is equal to the front plus 1. So we're going to move the front. But we also want to return the front to the beginning of the array if we have reached the end, right? So in order to do that, I'm going to say that this is going to be the remainder of front plus 1 by the capacity, right? And I'm going to explain in just a moment why I'm doing this. Then, of course, I'm going to decrement the rear, and then I'm just going to return here the value that I just dequeued. All right, so let me explain here this line. So I'm going to open here my whiteboard. And imagine that my queue is going to be this array right here. And imagine as well that it has 10 positions. So here is 0 and here is 9, for example. Now, when you calculate the remainder of something by 10, so the remainder of n, for example, by 10, this is going to give you a number between 0 and 9, right? Because if you divide 10 by 10, that's just going to give you 1 and the remainder is 0. So if the front plus 1 falls inside of any of these indexes inside of the bounds of the array, it's just going to be a number between 0 and 9, and it's just going to remain the same, right? For example, if front plus 1 is equal to 8, 8 modulus 10 is going to be just 8, right? The result is going to be 0, the remainder is going to be 8. And that is true for every number between 0 and 9, essentially. However, if our front plus 1 falls outside of the array, so for example, at the position 10, now the remainder is going to be 0, right? Because 10 remainder 10 is going to be 0, and the result is just going to be 1, right? So what this does is it actually grabs the front and puts it to the front of the array, right? It basically creates a circular motion of the front pointer, so that when it reaches the end of the array, it just goes back to the beginning like I told you, right? So that is why we're doing that line right there. So I only have two more methods to show you. The first one is going to be a void, is going to be called getFront, and this is going to get the front element of the queue. I'm actually going to go up here and grab this because it's the same verification, right? If the queue is empty, we don't really want to do anything. And otherwise, I'm going to see out the queue at the position front and then a \n like so. So this is going to get the first element of the queue, the front of the queue, right? And you can also do this with the back of the queue, with an index in the middle of the queue, and anything you want. All right, so the last one is going to be a display queue method. This is just going to basically allow us to see our queue, to see the elements in our queue. It's the same verification once again. If the queue is empty, we don't want to do anything. Otherwise, we're going to iterate. So we're going to say int I is equal to front. I is smaller than or equal to the rear, because the rear is actually going to hold a value as well. And then I++, I'm going to see out my queue at the index I, and then a little separator, dash, and then an arrow like so. And in the end, I'm going to see out here a \n. All right. So I think those are all of the methods I wanted to show you. Now let's actually create here a queue. I'm going to say queue is equal to queue with a capacity of 10. So we're going to have a maximum of 10 elements here in our queue. Then I'm going to say queue.inQueue to add a couple of elements. Let's add, for example, 10. And I'm going to add a couple of elements here to my queue. And then in the end, I'm going to call here my display queue to see what it gives us. Let me pull this up. All right, and there we have our queue. Now let's call the dequeue method. This is hopefully going to take 10 from the queue and return it. So if I run this, there you go. Now 10 is no longer in the queue, and 19 is also not in the queue. Let me see what that is about. Hey guys, so I made here a mistake. This is not supposed to be here. I don't know why I did this. I guess I was thinking about removing from the end, but we're actually removing from the front. We're not supposed to decrease the rear, right? So hopefully now this is going to work. Let me run that. And all right, so now 19 is over there. Perfect. So I apologize for that mistake. It happens sometimes. The last thing I want to do is get here the getFront method and call that. And I'm going to run this like so. And this is going to get 15, the front element of the queue. Perfect. So once again, I apologize for the mistake, but essentially that's all I wanted to show you in this video. In this video, I'm going to talk about the stack data structure. So this is a data structure that follows an idea called FILO, and this stands for first in, last out. Essentially, what this means is that the first element that you put in the stack is going to be the last that you're going to take out or process. So I'm going to give you an example of a stack of plates. You're always going to put the plates at the top of the stack, right? And if you want to remove a plate, you're going to grab the plate at the top and remove it. So essentially, the first plate that you put in the stack is going to be the last plate that you're going to take out or use or clean or whatever you want to do with it, right? So that's the idea of a stack. Now you could implement this using a linked list. However, I'm going to teach you how to implement it using an array. So this is really easy. Essentially, the array is going to have a bunch of indexes, and you're going to have a variable called top, which is going to store the top index of the stack, right? So if you want to add an element here, you just grab the top and you move it up. You want to add an element here, you grab the top, you move it up, right? So if all of these are filled, then the top is going to be up here, right? And if you want to remove an element, you grab the top and you move it down, right? And you don't really need to do anything to the element that you've just removed, because the stack is only going to be below your top, right? Anything that's over your top is not going to be inside of the stack anymore, right? So for that reason, you can only really add or remove elements from where the top is, right? So that's the idea of the stack. Now let's actually implement this in code. I'm going to represent my stack with a struct called stack, like so. In here, I'm going to have a couple of attributes. First, a top, which is going to store the top of the stack, and then the stack itself, which is just going to be an array of length max. I've defined it to be 100 up here. Then we're going to have our constructor stack like that. And in here, I'm just going to say that the top in the beginning is going to be -1, right? So in the beginning, the stack is going to be empty. Now I'm going to have a method here, which is going to return a Boolean. I'm going to call this isEmpty. And in here, I'm going to check if the stack is empty or not. In order to do that, I'm just going to return top is smaller than 0. So why does this work? Well, that's because we're going to increment the top when we add elements, and we're going to decrement the top when we remove elements, right? So the stack is going to be empty if the top is smaller than 0. All right, then we're going to have here a method called push, and this is actually adding here elements to the stack. First, we're going to have here the value that we want to push, and inside of here, I need to check if I have positions left. How do I do that? Well, I'm going to say if the top is greater than or equal to my max -1, that means that the stack is empty, right? So it doesn't really make sense to put more elements inside of the stack. I'm going to see out here \n and then stack overflow like this, and then a \n, and I'm just going to return because I don't really want to do anything. Now otherwise, I'm going to say that the stack at ++ top is going to be the value. So essentially, I'm going to increment the top and I'm going to put the value in that position, and that is the push method. Then we're going to have pop, which is removing an element from the top of the stack, and this is going to return to us the element that we are removing, right? I'm going to say if this dot is empty, like so. So essentially, if the stack is empty, it doesn't make sense to remove an element from the stack, right? So I'm going to see out stack is empty, ! Like so. And this is going to tell us that the stack is empty, and I need another \n here. And then I'm just going to return 0 as a code to tell us that something went wrong, right? Then I'm going to say that int value is going to be the stack at the top, so essentially the element we're going to remove, and I'm also going to decrement top, and then I'm just going to return the value. So this is the pop method. Then we're going to have a peek method, and this is just going to return to us the element at the top of the stack. Now I'm actually going to grab this because it's the same verification, and I'm going to paste it right there, right? If the stack is empty, it doesn't really make sense. And otherwise, I'm going to say that the int value is going to be the stack at the top, and I'm going to return the value like so. So this is how you see the top of the stack essentially. Then the last method I'm going to have is going to be a display stack like so, just so that we can see the elements in our stack. I'm going to say for int I equals 0, I is smaller than top, and I forgot I++. Let's say see out the stack here at the position I and a \n, and this allows us to see the elements of our stack. All right, so that is the implementation of the stack. Let's actually see if this works. I'm going to create a stack S here like so, and let's put a couple of elements here in the stack. So stack.push, and what is this telling me? Okay, so this is not these parentheses. I need to call the constructor. Okay, now I'm going to push a couple of elements, and then I'm going to display my stack like so. And let's run this to see if it works. Let me pull this up. And this is our stack. We have an element missing. Okay, because this needs to be smaller than or equal because the top is also going to have an element. Let me run this again. All right, and now we can see our stack. Now let's use the pop method. This is going to remove an element from the top of the stack. So it's going to be 21 in this case. Okay, so 21 is removed. And then I'm going to see out stack.peek and a \n, and hopefully this is going to give us 13. All right, so it gave us 13, the element at the top of the stack, and then the elements in the stack.